Hi, and welcome back to The Joy of Ray Tracing, a video series in which we make several ray tracers from scratch. On the last episode, we learned how to raycast a plane in 3D, and by the end of that episode, we were able to add a simple ground plane as well as a background gradient sky color to our scene. Now on today's episode, I'm really excited because we are going to learn how to intersect a ray with a sphere in 3D. And raycasting a sphere is one of the most important concepts that we can learn when making our ray tracers. Rendering spheres is at the very core of all the classic ray tracers from the 1980s and 1990s. And so, since this topic of ray tracing spheres is so important to all ray tracers, I'm going to take some time today to go over all the concepts that we need in order to understand how to intersect a ray with a sphere and render that sphere in our scenes. And hopefully by the end of today's episode, you'll have a good understanding of where the algorithms and formulas for ray tracing spheres come from. So I'm really excited to show you all that today. So let's take a look at what we're going to do today. Today's to-dos. Now before we start learning how to raycast a sphere, we first have to take a look at another aspect of the dot product. And if you recall from last episode, we learned all about the dot product and what it means to multiply two vectors together. But today we're going to see what happens when we take the dot product of a vector and itself. And we'll see how this crops up in the formulas that we're going to use for intersecting a ray with a sphere. Next, we'll see how a sphere is defined in 3D and what basic components it needs when we want to create different spheres of varying sizes and to be able to position the sphere anywhere in our scene that we like. And I'm a visual person, which is partly why I like computer graphics so much. So before we dive into all the formulas and math required to ray trace a sphere, I want to first take a look at what we're trying to do visually. And hopefully by looking at some pictures of different rays intersecting a sphere at various points, we'll get some intuition about what happens when we try to intersect a ray with a sphere. Okay, so I have good news and bad news. I'll give you the bad news first. The bad news is that this episode will contain the most math of all the episodes in this series. And that is because the ray versus sphere intersection algorithm contains a lot of calculations. So there's no escaping that. But the good news is that once we understand the formula for intersecting a ray with a sphere, we can simply let the computer do all the calculations for us. And that's what computers are good at. But like I said at the beginning of this episode, the ray-sphere intersection is so important to all ray tracers, old and new, that I think it's really important that we understand where all these formulas and algorithms come from. And even though there's quite a bit of math involved in deriving the equation for ray versus sphere intersection, like I mentioned before, once we have the formulas and the algorithms typed into our code, then we can just forget about it and let the computer do all the work. Which brings me to our next bullet point here. We're going to add that ray-sphere intersection routine to our JavaScript math utility library that we've been working on for the last couple of episodes. And if you recall from last time when we learned how to intersect a ray with a plane in 3D, that there was quite a bit of math with that too in the beginning, but once we got to the code, it was actually just a handful of lines of code. And the ray intersecting sphere routine is no different. So although we'll have to do quite a bit of math to derive the formula, once we get to the code, it's only a handful of lines of code. And so the total number of lines of code today may be only like 25 lines of code. And we'll have the ability to ray trace a sphere of any size and in any position in our scenes. And as you know by now, I really like doing at least some graphics programming on every episode. And so after we've gone through all the concepts and the math and the algorithms and adding ray versus sphere intersection to our code, then we can have some fun by adding a sphere to our ground, plane, and sky scene that we did last time. So I'm really excited to see that today. So let's get started. All right, I'm going to go into my OneNote app here. So before we get into the technique of raycasting a sphere, we need to take a look at one more aspect of the dot product. So on the last episode, we learned that the dot product was one of the ways in linear algebra where you can multiply two vectors together. And let's quickly go back and take a look at how we do the dot product. And last time we learned that in order to take a dot product between two vectors like vector u and vector v, you take the x component of vector u, which is the first vector, and then multiply it by the x component of the second vector, which is vector v. So you have ux times vx, and then that is added to the y component of the first vector times the y component of the second vector. So uy times vy. And remember that we had said last time that the dot product operation gives you back a number. So even though you start out with two vectors, they could have any number of components. So you could be in 2D like this, which is x and y components, or you could be in 3D, which is x, y, and z components. But when you take a dot product of any two vectors, you always get back just a simple number or a scalar. So now let's return to today's topic. And that is, what happens when you take the dot product of a vector and itself? Does that even make sense? And can we use that somehow in our ray tracers? Well, the answer to both of those questions is yes. Taking a dot product of a vector and itself is a valid operation, and as we'll see, is quite useful and crops up in some of the most unlikely places. So here we have vector v, and remember we put a little arrow over that to denote that it's a vector, and we have vector v dot vector v. And over here on the right, I have an example of the vector v that I previously drew out, and I made vector v lie flat on the ground in the positive x direction, going to the right. And this will just make the math a little simpler for our whiteboard here. So let's go ahead and write out the dot product of vector v and itself. So recall we take the x component of the first vector times the x component of the second vector, which is again vector v. So we just do times vx again. Next comes the addition symbol. And now we do the same for the y components. So the y component of the first vector, which is vector v, times the y component of the second vector, which is also vector v. So we just do vy again. Now let's just plug in the values for vector v over here on the graph. The x component of vector v is 4, because we have the vector v as 4, 0. Those are its x and y components. So let's fill in a 4 here, times, now the x component of vector v again, so we do another 4, and put that in parentheses, because that has to be done first in order of operations in math. So you do the multiplications first, and then you do the additions later. Plus, now let's take a look at the y components of vector v, and over here we see that the y component is 0, because it's lying flat in the x direction. So I'll write 0 times 0 again. Now we can just simplify. So 4 times 4 is 16, plus 0 times 0 is 0. And that equals an answer of 16. And recall that when we do a dot product between two vectors, we always get a number back. no matter how many components those vectors have, x, y, z, it could have 27 components. It doesn't matter. When you do a dot product between two vectors of any size, then you get back just a simple number or a scalar. So this 16 as the answer might not seem all that important right now, but let's look at the dot product in a different way. And recall from last time that we said that the dot product of a vector with another vector is kind of like projecting the first vector onto the second vector. And if you're uncomfortable with thinking about projections of vectors onto each other, I like the analogy of shining a bright light on the first vector and then casting its shadow onto the second vector. So that visually for me, it makes more sense. And so over here on the right side, I drew out a picture of a bright light source. Let's say it's the sun. And the sun is at high noon, so it's straight up in the sky. And so it's casting its light downward like this onto vector v. And vector v will cast a shadow onto the second vector. But in this case, it is the second vector also. It's a little weird on this analogy of taking the dot product of a vector with itself, because it's kind of like casting a shadow on itself. So I drew the shadow just a little lower so you can see it, but actually this shadow right here, this purple shadow, would be right in line with the red vector, vector v. And let's go back to the original dot product slide. And here we have a typical case of vector u and vector v that are different vectors. But when you shine the light down from the top and it casts a shadow of u, but the shadow may only cover part of vector v. And also recall that the direction of the sunlight or the direction of the projection has to be at right angles with the second vector, or the one you're casting the shadow on. So in this case, vector v is lying flat in the x direction, and then we have the sun straight up, so that makes a right angle with the light source and the vector that we're projecting onto or casting a shadow onto. So over here we had done the traditional dot product operation and multiplied the x components and then added the multiplication of the y components. And that equaled 8 in this case. But then as I showed you, you can also think of the dot product as a projection or a shadow of the first vector onto the second vector. So when we look at it in that light, we can say that the dot product is the length of the projection, this purple shadow of u onto v, times the length of vector v itself. So we take the length of the shadow, so in this case it was 2, and then we multiply that by the length of the vector v that the shadow is falling upon. So the vector v was 4 units in length. So when you take the length of the shadow, which is 2, times the length of the vector v, and that's 4, and you multiply those together, 2 times 4 equals 8. And you get the same answer as we got by doing the component-wise multiplication, the x components and the y components. So it was an alternate way of getting the same answer, and also a different way of thinking about what the dot product is doing visually. So let's go back to our current topic, which is taking the dot product of a vector with itself. And so we had said that another way of looking at the dot product is you take the length of the shadow that it casts, and then you multiply that by the length of the vector where the shadow is falling. So in this case, it's going to be vector v's length. So let's just write that out real quick. The dot product is also the projection of vector v onto vector v, because it's casting its own shadow on itself, multiplied with the length of vector v. So now let's just plug in those values. So the length of the purple projection, or the purple shadow right here, is 4 units, times the length of v, or the vector where the shadow is falling. So we just use the vector v again and get its length. And that's easy to do. Since the y component is 0, we can just look at the x component, and that's 4. So we know it must be 4 units long. And so the length of vector v is 4. And when you multiply 4 times 4, you get 16, which is the same answer we got by the traditional method of the dot product. Now, the reason it helps to think about it in this manner, which is the shadow times the length of the vector where the shadow is falling, is that since we're taking the dot product of a vector with itself, its own shadow is going to be as long as the original vector is. And so we don't even have to worry about projecting the vector or casting a shadow, because we know that the shadow is going to be the same length as the vector itself. And so in order to take the dot product of a vector with itself, you simply just multiply its length times its length. So in this case, the vector v was 4 units in length. So we take the length, which is 4, times the length, which is 4. And you have 4 times 4. And in math, when we multiply a number times itself, we usually say that number is squared. So it will have an exponent of 2. And so this is the important part. We come to the conclusion that a vector dotted with itself is equal to the length of that vector squared. And hopefully that makes sense intuitively. So if you have 4 squared, that equals 4 times 4, which is 16. And so in linear algebra, when you take the dot product of a vector with itself, it's kind of like multiplying the vector by itself. And so we would expect that we would get some kind of squaring operation out of that process. And likewise, if you see a vector squared, it is the same thing as vector v dotted with vector v. So if we see v squared somewhere in a formula, or if we see vx times vx plus vy times vy, and so on, we can just simply rewrite that as v.v. And later, as we'll see, when we get to the formula for a ray versus sphere, we'll see a couple of vectors that are squared. And knowing this now, we can just go back and say, well, if we see a vector squared, we know that that's simply just v.v. And we can just call that function from our math utility library in JavaScript. And before we move on, I mentioned that this crops up in an unlikely place. And so if you look at the traditional way of doing the dot product of a vector and itself, which is its x component times its x component plus its y component times its y component, that seems awfully familiar. Where have we seen that before? I know I've seen that somewhere. Well, let's go quickly into Visual Studio Code and take a look at our math utilities. And hey, look at that. There it is. The x component times the x component plus the y component times the y component. And since we're in 3D in all ray tracers, we add on the z component times the z component. And then we take the square root of all that and we get the vector length. And we had said last time that the vector length itself comes from the Pythagorean theorem. And so this bit right in here is like taking the dot product of this vector with itself. So this bit of code right here that I've highlighted will give you the vector's length squared. And so that's why we have to take the square root of that to get the actual vector length that we're interested in. If we didn't have this square root operation right here, we would just get back the vector length squared. And that is in line with what we had just said about the dot product with a vector and itself, is that when you take a dot product of vector v with itself, you get its length squared. Now, I think this is just a happy math coincidence. I don't think that Pythagoras had the dot product in mind when he came up with the Pythagorean theorem. And likewise, I don't think the creators of the dot product had the Pythagorean theorem in mind when they devised a way of multiplying these components of the vectors together and then adding them all up. So I think it's just a happy coincidence that we find the dot product embedded inside the Pythagorean theorem. But I think it's really interesting that the dot product crops up in these unexpected places like that. And we'll see in a moment how we can use this length squared to our advantage when trying to intersect array with a sphere and dealing with the formula for that. All right, so since today's episode is all about spheres and raycasting spheres, let's take a look at how a sphere is defined mathematically. So on this whiteboard, I drew out a purple sphere. And don't worry about the P point here just yet. We'll get to that in just a sec. But notice that the sphere has a center that's located at the world origin, which is 0, 0. So that center is denoted by the letter C. And then you'll see there's an R here that it's in a pink color, and R stands for radius of the sphere. And in this case, I made the radius equal to 2 units. So if you follow from the center of the sphere out to the edge of the sphere, then you go 2 units, or its radius in length. And the reason why spheres are used so much in the early days of ray tracing in the 1980s, when graphics researchers were just starting with ray tracing, is because the sphere itself is one of the most simple shapes you can have in geometry. All you need to be able to define a sphere is the center point of the sphere and a radius from the center out to the surface of the sphere. So to define any sphere in 3D, all you need is the center point, which is a vector. It may have x, y, and z components. And then you just need a simple number, which is the radius. And that'll be the distance from the middle point of the sphere out to its surface. So just with those 2 bits of information, you can define any sphere. Now let's go quickly back to the definition of a plane that we did last time. And recall from last episode, we said that the plane also only needed 2 bits of information. So it needed a center point where the plane origin is, and it needed a normal vector which points away from the plane or perpendicular to the plane. And so it needed 2 types of vectors, one that's a point and one that's a vector. And then you could define a plane using an implicit equation. And so we had said that this implicit equation, once you plug a random point into this implicit equation, you should get 0 as a result. And so we tested the point P here, and we put that inside of this plane equation, and we went through the math and we got 0 in the end. So we determined that that point P was definitely on the plane. Now likewise, we can go back to our sphere, and just like the plane had an implicit equation, the sphere also has its own implicit equation. And so let's write that out now. So the implicit equation for a sphere, you take any point that's on the surface of the sphere, so we'll call this point P, and you take its x component and square it, and then add its y component squared, and then add the z component squared. Because we're in 3D, remember, spheres are 3D, whereas a circle is just 2D. Pz squared. Then you subtract the radius squared, which in this case is the lowercase r right here. So I'm going to write that in the pink color, and that's squared as well. And then when you do all those calculations, your result must be 0. And I'll write up here that that is the implicit equation. So why is it implicit and not explicit? Well, remember that an implicit equation doesn't generate points for you that are on the sphere. All it does is provide a handy test or you can test a point if you already have a point. And so you can take a random point that you choose and see if it's on the sphere or not. So this equation, px squared plus py squared plus pz squared minus r squared equals 0, is implicitly defining the sphere, because you can test a point of your choosing against this equation. And if it equals 0, then you know for a fact that the point that you chose is definitely on the sphere itself. And one quick side note is, take a look at this, px squared plus py squared plus pz squared. So that's like saying px times px plus py times py plus pz times pz. That looks familiar. Where have we seen that? That's kind of like taking the dot product of vector p with itself. So its x component times its own x component, plus its y component times its own y component, plus its z component times its own z component. And once again, we see the dot product of a vector in itself crop up in the most unlikely place. So it turns out that when you implicitly define a sphere in 3D, it's kind of like taking the dot product of the point that you choose with itself. And in fact, another way to write this is the length of p squared. And so if we wanted to, we could write this implicit equation of a sphere in vector form. And then in that case, it would have p squared, or p dot p. And yet another way we could have written it is p dot p. So the vector p dotted with itself equals the length squared equals px times px plus py times py plus pz times pz is also equal to px squared plus py squared plus pz squared. All this writing in blue is saying the same thing. So in fact, if we wanted to, we could write this implicit equation of a sphere in vector form. And then we could write p dot p minus r squared equals 0. So, and you might see that in some textbooks on ray tracing or some graphics programs out there. But I'm going to leave it in the standard form, which is the first one here, because that's going to help us when we want to do the algebra in a moment, when we actually expand these terms. I want to be able to see the x components individually from the y components, individually from the z components. And so we can kind of separate all those out and then simplify, and then we'll end up with a nice equation at the end. But just be aware that this notion of taking a dot product of a vector with itself crops up in all sorts of places. So I'm going to get rid of these alternate notations here. So going back to the standard form of this equation, it's saying that if you've defined a sphere with a center location and a radius, that you can take any point that you want to test and plug it into this equation, and it should give you back 0 if the point is on the sphere. Just for a simple example, I made a point called P, and it is located at 0, 2, 0. And visually, we can see that this point is definitely on the sphere because it's 2 units up, and our radius was 2, so it must be on the sphere. But we would like to be able to move this center point all over the place and still have this equation work. Because let's say I moved the C center point of the sphere up 1 unit. So now it's 0, 1, 0. That would make this P point that I had picked also up 1. So it would be 0, 3, 0. Now, if you plug that into this equation, it's not going to work because you'll get 3 here, and then the radius will still be 2, and those won't match. And so this will not equal 0 when you plug all those numbers into this equation. So essentially, we have to remove the offset of the C point, or the center of the sphere. We have to take that back off to get the P point back into world center coordinates, or back to the origin of the world, 0, 0, 0. So we have to put the P point in terms of a sphere that is located at the world origin, even though the sphere itself may be anywhere out in the scene. So how we do that is just to simply subtract off the C. So we can take this P point here and just minus C, and then that'll put the sphere back into the world origin of 0, 0, 0. So it's like we removed that offset. And so how we do that mathematically is we subtract all the C components from the P components. So we write Px minus Cx, and then put that in parentheses because that has to be done first, and then square all that. And then we continue in a similar fashion. So we take the y component of point P and subtract the y component of the C point, and then square that. And then finally we do that for the z component as well. Pz minus Cz. And I ran out of room here, so I'm going to make this smaller so we can fit it all on this line. There we go. And then square that as well. And then finally we subtract the radius squared, and that should all equal 0. So now we have Px minus Cx squared plus Py minus Cy squared plus Pz minus Cz squared minus r squared equals 0. So although that complicated the equation a little bit and it looks a little more messy now, this will allow us to move the sphere anywhere we like. And so we consider that as like an offset. So it begins at the world origin, which is 0, 0, 0. And then we can move it anywhere we like. We can go up, down, left, right, or forwards and backwards. And then this little trick we did over here of subtracting the C center point of the sphere essentially removes that offset. And so it brings everything back into the relationship of 0, 0, 0, which is at the world origin. And then all the math will work out. If the point is indeed on the sphere, then when you do all these calculations, you will get 0 in the end. And so let's go ahead and try that out for ourselves. And I'm just going to plug in all these numbers here that we have, and let's see if it equals 0 in the end, and let's see if point P is indeed on the sphere. So first we need the x component of P, so that's 0, minus the x component of the sphere center, and that's 0, and we're going to square that result, added to the y component of P, so that is 2, minus the y component of C, and that's 0. Because remember, C is just 0, 0, 0, so it always has zeros in this case. Oh, and don't forget to square that, and then plus the z component of P, which is 0, minus the z component of C, which is again 0, and we're going to square that, minus r squared, so let's fill in that, so 2 squared equals 0. Now let's just simplify these. So we'll do the parentheses first, so 0 minus 0 is 0 squared, plus 2 minus 0 is 2 squared, plus 0 minus 0 is 0 squared, and then finally minus 2 squared equals 0. And hopefully you can see by now that this is going to work out, but let's just, for sake of clarity, let's just go ahead and finish it out. So 0 squared is 0, plus 2 squared is 4, plus 0 squared is 0, minus 2 squared here is 4, equals 0. And then here we have a positive 4 and a negative 4. So 4 minus 4 is indeed equal 0. And we're left with 0 equals 0, which is true. So I'll get my green marker here, and we get a big check mark. So point P is definitely on the sphere. Now, since the C point was at the world origin, which is 0, 0, 0, this subtraction right here didn't really make a difference because we ended up just subtracting off zeros each time. But if you move that C point anywhere else, so if you move your sphere around the scene, then we're going to need to do this, and it will matter in the end. So if this was moved up by 1, then you need to take that 1 back off when you do the calculation, and then everything should be put into back into the world origin coordinates, and everything will work out. So you'll get 0 equals 0 at the end. So everything should be equal 0 if the point is indeed on the sphere. And that's no matter where the sphere is or how big it is. And so hopefully this makes sense intuitively. So this implicit equation just provides a simple test for whether a point that we pick is on the sphere or not. It does not give you a point on the sphere. Instead, it provides a test for a point that you pick. And we will use this implicit equation in our upcoming formula when we want to find out if a ray intersects the sphere. So let's take a look at that now. And just for a moment, let's go back to our ray plane intersection that we did last time. And so here you can see the plane, and we have an implicit equation for the plane, and that was a point on the plane minus the plane's origin dotted with its normal should equal 0. And that's how you could tell if a random point that you pick is on the plane or not. But how do we come up with this point? Well, it's where the ray will hit the plane, if it hits the plane at all. And so recall that the ray has what's known as an explicit equation. And so the difference between implicit and explicit is the explicit actually generates a point in 3D space. If you look at this equation here for the ray, it says a point along the ray equals its origin plus a scaled direction of the ray. So in this case, we did not provide the point, this 3, 0, 0. Instead, it was generated by the ray equation. And how it is generated is that we provide this little green t value right here. And the explicit equation is also known as a parametric equation because you provide the parameter t, and that moves the little point up and down the ray. And so if you give it a bigger t value, then it'll move it farther down the ray. And if you give it a smaller t value, it'll stay closer to the ray's origin. And so much like our plane had an implicit equation, whereas our ray has an explicit equation, our sphere has its own implicit equation where you can test, but the ray still has the explicit equation where you generate a point by giving it a little t parameter. And the magic of ray tracing and ray casting in general is that you can combine these seemingly disparate equations into one equation that will solve for the t value. So on the next slide, we took the plane equation, which was this, and then the ray equation, which was here, and we simply replaced the point here in blue with the ray equation. So where you see the blue writing here, we replace that with the equation for the ray. Once we've done that, then our job is to get t on one side of the equation, and then we can solve for t. And once we feed that to the computer will give us back a t value, and if that t value is a good positive number, like greater than 0, then we know that we hit the plane. So it's going to be very similar in our sphere case now, that we have an implicit equation for the sphere, but an explicit equation for the ray. And we're simply going to take the ray equation and plug it in to the sphere equation, and then isolate t as much as we can and solve for t. And if we get back valid t values, like positive numbers greater than 0, then we'll know if we hit the sphere or not. So let's go now to the ray sphere intersection part 1. And for now, don't worry about these green dotted lines and these 4 cases over here. I just pre-wrote those out because in the interest of time, I don't want to have to sit there and draw all these dotted lines on camera here and have you painfully watch me try to be an artist. So I went ahead and made some diagrams here so that we can more quickly get to the concepts. And so here is a reminder, we have the sphere equation, which is implicit. It says px minus cx squared plus py minus cy squared plus pz minus cz squared minus radius squared should equal 0. And then over here, we have the sphere in purple again, and then here's the C center point of the sphere. So that's the location of the sphere in 3D space. And then we have R over here in orange color, and that's the radius from the center out to the edge of the sphere. Now notice that this equation doesn't give you a point on the sphere, it just provides a test, right? So, and then we have our usual ray equation, which is always explicit. So the ray equation says that any point along the ray, which is, I'll denote P, equals its ray origin plus its direction scaled by a t value. And this t is also known as the parameter. So it's a parametric equation. We're actually giving it a parameter and then generating a real point along that ray. And I tried to stay consistent with my coloring here, so you can see the ray origin. I have a couple of examples of different rays in different locations, and so this pink color here is reserved for the ray origins. And so you can see it right here on number 1, and then case 2, case 3, and then case 4. So those are 4 different locations of the ray origin, and that's just a point in space. And then we have the yellow vector, which is its ray direction. And so that's a little direction vector, and that's denoted by a yellow arrow. And so you can see here, each origin has its own little arrow attached to it. So all these rays, 1, 2, 3, and 4, they're all pointing in the same direction. They're all going up and to the right. And so you have an origin, direction, origin, direction, origin, direction, and origin, direction. So 4 instances of a ray. And now if you look at this t, the green t value here, notice that we don't necessarily know what that is. So we do know where the origin of the ray is, and we do know the direction of the ray. We define that ourselves, but we don't know the t value. So we don't know how far the ray will go until it hits a sphere. And so now let's take a look at these green dotted lines that I had previously drawn out. So let's take a look at case number 2 here first, because that'll help us realize something unique about this spherical shape in rays. And imagine this ray is traveling up and to the right, and it does hit the sphere here, but it also hits the sphere on the backside. And so the ray has an entry point to the shape and an exit point on the other side of the shape. And so now that means that we can have 2 possible t values. And so this is a valid t value right here on the entry point, and this is also a valid t that's on the exit point of the sphere. Both would be positive numbers because they move the ray in a positive direction along its direction vector. So since this ray or this line crosses the sphere at 2 points, that's going to mean we're going to get 2 t values back, and therefore the surface itself is quadratic in nature. So anything like a sphere or an ellipsoid or an open cylinder or an open cone, those are all examples of quadratic shapes. So if you make a line pass through the shape in any direction, then the line will touch at exactly 2 points if it does intersect the shape. And so that's why we have these two t values, and I had to name them t0 and t1. We can't just refer to it as t anymore, because unlike the plane where we had one point of intersection, so if you have a plane and you have a ray coming in, and it can only hit the plane at one point. It doesn't cross back out the other way. It doesn't cross the plane twice. It only intersects the plane at one point exactly. But if you have a sphere, now you're going into the entry point of the sphere on the front of it, and then you're also exiting out the back. So you have two possible intersection points that you need to deal with and handle in your ray tracer. So now let's go over here where I made a little table of all the cases that can go on when you try to intersect a sphere with a ray. And we were looking at case number 2, where it entered here and we got a t0, and then it exited here and we got a t1. So now let's look at case number 2. t0 will be greater than 0 when we do this calculation. And then also we'll get another t value, which we'll name t1, and that's also going to be greater than 0. So which one do we pick? Which one is the correct one? Well, in ray tracing and in general, it's always the one with the least t value. So the minimum t value will always win. And so we want to know at what point does the ray first intersect the shape. We don't really care about the backside of the shape because we can't see that anyway if it's a solid shape. So we want to know where's the first time that that ray will intersect the shape. Therefore, I'm going to write over here that we should pick the intersection equals t0, because t0 is the least of those values. t0 will always be less than t1. And so we always want to pick the t value with the closest distance to us, or the least distance. So in case number 2, if we get back a t0 and a t1, both that are greater than 0, and they're both good, then we should pick the t0 and disregard the t1. Even though the t1 was a valid intersection point, it was just on the back of the sphere, so we don't really care about that one at this point. And I'll put a green check on this case. So case number 2, we have a good intersection. Now let's look at case number 1. And I named this case number 1 because this is actually going to be 90% of the cases. So if you have like a little sphere in your scene and it's sitting on the ground, let's say, and you're firing out a ray from each pixel. Remember how we did that last time? We fired out a ray. And what we want to know is, do those rays hit the sphere or not? Well, if the sphere is in the middle of your screen, it's only occupying just a little portion of your screen. And when you send out all those rays, chances are most of them will hit the sky or the ground. And so they're not going to even hit the sphere at all. And how do we know that though? Like, how do we know that mathematically? And so when we do all this math, and coming up in a moment on the next slide, we will get back a t0 and a t1. Both will equal infinity for t. And so if we do these calculations and we plug in the ray equation to the sphere equation, and we get back an invalid t value, so infinity, then we know that no matter how long we move the point along the ray, it'll never intersect that sphere. And visually we can see that by noticing that the ray is a little too high. It's pointing in the right direction of the sphere. It would have hit it if it was a little lower, but it's a little too high and it goes over the top of the sphere. And so in that case, if we get infinity back from our equation, then we know that there is no intersection. And I'll get out my red marker here and make a big X. So case 1 failed to hit the sphere. Case 2 worked out, so we took the t0 from the two values that we got back. And now let's look at case number 3. This is an interesting one. So let's say you do this equation that I'm about to do on the next whiteboard. I'll get to all that math later. Let's say you do that and you get back two t values, so you don't get infinity. You know the ray hit the sphere, but your t0 is less than 0 and your t1 is greater than 0. So now how do you handle that case, and what does that mean? Well, if you look here, we have the slope of the ray's direction that goes up and to the right. And if you treat it as a line, an infinite line, it does hit the sphere correctly in two places. It has an entry point and an exit point. But this point here, generated by the t0 value, is behind the ray. So technically, we can't see that with our ray that we shot out into the scene. And as I said on the last episode, we never want to use a value for t that's less than 0. That doesn't make sense because that means the point is behind us, and we don't care about stuff that's behind the ray. We only care about stuff that's in front of the ray, or that it will hit in the future. And so in this case, we have to reject t0 and use t1 because that's the only valid intersection remaining. And so what does that mean? Well, it means that our origin of the ray started inside the sphere. And so imagine yourself as a ray, and you're surrounded by a huge sphere, like a big dome. And so you send out a ray from yourself in a direction. Now, you're going to get two intersection points back. You're going to get one that's behind you on the back side of the sphere, behind where you can't see. And then you're going to get a second intersection point that's in front of you. And so we don't care about the one behind us because we can't see that. But we care about the one that hits the ceiling of the sphere or the top of the sphere if you're looking up. And so we would choose the second one. And so now on this one, this case number 3, we're going to choose the second one, which is T1. So I'll write intersection equals T1. And I'll put a big green check mark because that was a valid intersection, so it was a success. So that's a little more rare that you end up finding yourself inside of a sphere and you want to render the inside of a sphere, but we might have to do that in future ray tracers if we have, like, say, a glass sphere or a glass object and we're located inside of that object, and we might want to see what's beyond that object. So we might want to intersect it with the inside of that, or the interior of that big object, and then go out into space or go out into the sky or something like that and see what's beyond that object. So there will be times when we need to start the ray inside of an object. But for today and most of our ray tracers in the next episodes, we're going to be just generating rays on the outside of the objects. So most of our cases will be the number 2 here, where we see the front of the sphere, or where we don't hit the sphere at all, this number 1. So we just keep the ray going and check for other objects. And then finally, let's look at case number 4. This is another thing that can happen when we plug in these equations to each other. So let's say we get a T0 and T1 that are not infinity, so we know that it hit the sphere, unlike this case here where they're infinity. So let's say we get a number back, but both T0 and T1 are less than 0. And so they're both negative. And what does that mean? So if you look here on case 4, the ray origin starts over here, and the slope of its line, or its direction, correctly intersects the sphere at 2 locations. So it gives us back 2 good locations. But the only problem is they're both negative, because if you can see, the 2 blue intersection points are behind the ray where it's looking. And so that would be like placing a sphere behind you completely and then casting out a ray. Well, that ray is never going to hit in the direction that it's going, but it will hit behind you. But remember, we don't care about stuff that we can't see behind us. And so in this case, if both T0 and T1 are less than 0 or negative, then that is not a valid intersection and there's no intersection. So we'll write again, no intersection. And I'll get my red marker out again, and it gets a big X. So out of all these cases, only case number 2 and case number 3 can be valid intersections for a ray tracer. But like I said, most of our ray tracing programs at this juncture will either have a ray that misses the sphere completely, or it'll correctly hit in two places that are in front of the camera. And so we'll have a front side of the sphere and a back side of the sphere, and we'll just choose the front because that's closest to our eyes. So hopefully you can see from this diagram and our cases that we listed that we're going to need two t-values at the end of all this. And we can see that visually when we cross the ray's direction line with the sphere. If it successfully intersects the sphere, it'll intersect it at 2 points on the sphere. But how do we get two t-values back from these equations? And so it might not make much sense right now, and it didn't for me when I was just starting out in ray tracing, because like last time we had a simple equation for the plane. Let's go back to that real quick. So we had a plane equation that was implicit, and then we had a ray equation that was explicit and generated a point. And all we did was replace this point here in blue with this point here in terms of the ray. So we just wrote that here, and then you kind of stick the ray equation into the plane equation, and you're left with this longer equation here. But then you just isolate t through the magic of algebra, and so you get t on one side of the equation, and you solve for t. And we ended up with this nice little neat formula that we could call for every ray and correctly intersect rays with planes. But now I'm telling you that with a sphere, it's going to cross at 2 points, and so we're going to get two t-values. So how can we end up with an equation where we have t on one side of the equation and it gives us two different values? And if you're more experienced with mathematics, you might see where this is all going. But let's work through and actually plug the ray equation into the sphere equation and see what happens. So I'll go back to the sphere intersection. So here we have the sphere equation that's implicit, and it does not generate a point, but it just provides a check, and everything should equal 0 if the point P is on the sphere. And then we have the old ray equation that's explicit, and that always generates a point. So you give it a parameter, a single value like 1 or 2 or 27 or just a simple number, and it generates a point for you along the ray. And notice I used the same light blue color for the points in these equations. So point P is Px, Py, and Pz, and that could be any of these blue points. But we could also write those blue points in terms of the rays. We could generate those points with an origin of the ray plus a scaled direction. And so what we do is we plug the ray equation into the sphere equation, and we combine those two, and then we'll try to solve for t and try to get two t-values back. So the first step is actually splitting up the ray equation into its individual components. And so this is the ray equation in vector form. We have a point P equals the point R plus a scaled direction vector. So we need to split all those up into their x, y, and z components. So that way we can plug them in for these px, py, and pz coordinates that we see here in the sphere equation. So let's split this ray equation up into its individual components. So we're just going to rewrite it 3 times and then just do x, y, and z. So I'll start off with x. So this is the same thing as saying px equals the ray's origin x plus a scaled direction vector of the ray, its x component. So this is part of what this is saying here. So it's px equals ox plus t dx. And notice we use the x every time we had a vector. And notice I didn't put the little points over those anymore, or the vector little arrow symbol, because now this is just a number. So px is just a number, ox is just a number, t is a number that we provide, and then dx is a number as well. So there's no more vectors in this equation. It's just all scalars. And then likewise, let's split it into the y components now, doing the same process. So py equals origin y plus t direction y. And then finally, we'll do that for the z components. So pz equals oz plus t dz. And I'll write a little arrow here, meaning that this equation split up into its individual components is exactly equal to all these together. All we do is just split up these vectors into their individual components, and we're left with three numbers. So all of this will be a number, all of this will be a number, and all of this will be a number. So now that we split everything up into its individual components, we can go ahead and plug it in when we see px, py, and pz. So when we see those blue p values there, we just write it in terms of the ray instead. And then we'll have successfully combined the two equations together. So that's one of the coolest things about ray tracing, is that you can have an implicit formula for your shape that you want to ray trace. And then you can have your ray, which has the parameter, and that you provide the little t value that scales up the ray, up and down the ray's direction. And when you combine those two equations and then get t on one side, you can solve for t and get the points exactly where the ray intersects that shape. So that's one of ray tracing's greatest tricks. So I'm going to make a light blue squiggly line here. And so when we see px, we're going to write this instead, right, with the blue squiggly line under it. When we see py, we're going to write this. And when we see pz, we're going to write that, because they equal what the original equation said. This is going to be much longer now, so I'll try to make room. So I see a px first. So now we're up here. We're going to read this from left to right and just plug in the equations as we see them. So px equals ox plus t dx. So I'm going to write that first. And then continuing on with our sphere equation, it says minus cx. So I have to do that. And we're still inside these parentheses. Cx, that's the center of the sphere. Now we can close the first set of parentheses. So hopefully you can see that I replaced this px with ox plus t dx, because those two are equivalent. And that's how we're going to successfully merge the two equations. Now comes a squared exponent here, so we have to square all that, plus, and all we do is do the same thing for y, and then the same thing for z. So let's write all that out. So py right here is equal to oy plus t dy. So I'm going to write that. Oy. I'm going to move all this down here because it's going to get quite long. And now continuing on, it says minus cy. So I'll go ahead and put that in there. And all of that is squared. And now we do the same with the z components. So pz is equal to oz plus t dz. So I'm going to write that out. And then it says minus cz. And once again, all that is squared. Now at this point, I'm going to shrink this down just so it can fit. And then continue on with our sphere equation. It says minus r squared equals 0. So let's go ahead and add that. Minus r squared equals 0. Whew, that was a lot of math there. So let me make sure I did this right. So each time we see the px, we replace it with what px is in terms of the ray. So px equals ox plus t dx. So I have that here. And then minus cx, all that squared, plus, then we do the same for the y's. So oy plus t dy is right here, minus cy, all of that squared, plus pz, which is equal to oz plus t dz. So I put that down here, oz plus t dz minus cz, and then all that squared, and then finally minus r squared equals 0. So I think I got everything correctly there. Now, you may be worried that this is complicating this equation, and you'd be right, because now we have 3 terms inside of these parentheses, and all of those need to be squared. So now we would be doing a lot of factoring and things like that. But there is one simplification that we can do, and I'll show you on the next slide when we actually solve for t on this big long equation. We're going to simplify the like terms. So if you notice, there's an OX and a CX, an OY and a CY, and an OZ and a CZ. So we're going to combine those and make a new vector that's just one letter. Then we'll just have 2 terms in the parentheses instead of 3 terms in the parentheses. So that'll make it much easier to square those, because remember, we have to square everything inside the brackets. So, and I'm saving that for the next slide because I'm going to need the whole page to expand those brackets out. But we will make it a little easier than it looks right now. And so just looking at this, we're going to see that, there's going to be a t squared and then a t squared here and then a t squared there. So there is some notion that we could have multiple values of t, because remember, if you take the square root of 16, for instance, that could be 4. So 4 times 4 is 16. But another number that works is -4. So -4 times -4 is also 16. So the square root of a positive number like that has a positive answer and a negative answer too. And so you have 2 answers for the roots. And so by looking at these squared brackets here, we're eventually going to have something like t squared. And that'll mean we'll have multiple choices for what t could be. And that'll give us, hopefully, our 2 t values that we're needing to see where the ray intersects the sphere. Okay, so now at this point, it's the moment of truth. On the next slide, we have to expand all these brackets of this equation and try to get t on one side of the equation, as well as solve for t. And we already know going into it that we're going to have 2 possible t values, a t0 and a t1. So let's go to the big math slide now. So I can pretty much promise you that I'm going to fill up this whole screen with math. But remember, our whole point of doing all this math is not just to do the math, but it's to isolate t by itself as much as we can, and then eventually solve for t. If we can do that, we can intersect a ray with a sphere, and then we'll have glorious spheres all over our scenes. But in order to do that, the ray needs to know what its t value should be. And so we're going to simplify these equations and expand the brackets and simplify some more, and then try to get t on one side, and hopefully we'll arrive at a nice tidy equation that we can just plug into the code and then have the computer crunch the numbers for us, and then we'll get back beautiful spheres in our scene. So let's start out by taking a look at what we have to work with. And so I literally just copied these from the previous slides, so they should look familiar. Here's the sphere equation that's implicit, and then we have the ray equation, which is explicit. Now, you can't just stick this into this without breaking it up first. Right now it's in vector form, but we need to put it into component form. It's individual components. And then we can stick it into this equation because we have px, py, and pz. So now all I did was make this p vector here in blue. I just split it up into its individual components. So px, py, and pz. And then we copy this equation here and just put it in terms of its x components and y components and z components. And now that we have them in number form, or those individual components, we can stick those numbers back into here because we see px, py, and pz. So now on the next line, that's exactly what I've done. And so you can see where you see px before, now we have ox plus t dx. And then you just continue on with the equations. So it says minus cx, and then all that squared. And then you do the same for the y's and squared, plus the same for the z's squared. And then finally minus r squared equals 0. And so this equation is exactly the same equation as this. The only difference is we've replaced the p values with the p-values in terms of the ray. And this technique perfectly combines both equations. So you have an implicit and an explicit, and you wouldn't think that those two go together or you could combine them, but yet with the magic of algebra, you can replace things and combine equations like that and successfully merge the two equations where you can isolate the t values. So now our job as mathematicians at this point is to simplify as much as we can these terms and then square them. So we're going to have to expand those brackets and then simplify again and hopefully get to some kind of neat and tidy equation at the end of this, at the bottom of the page, basically, that will allow us to solve for t, or the multiple t values that we need, the t0 and the t1. Because right now, in its current form, we can't do anything with this. We can't just plug this into a computer and expect it to spit out an intersection point. It doesn't quite work like that. So we have to do some work before we give the computer the nice and tidy equation at the bottom here. So as I said before, we're going to combine the like terms, and that'll simplify the brackets just a little bit. And so you can see there's an ox and a cx, so those are like terms. And then we have oy, cy, and then oz, cz. So if we can combine those, that would make for less terms inside these parentheses that we have to eventually square. So what I'm going to do is create a new vector that will have x, y, and z components, and that will represent these subtractions. So ox minus cx, oy minus cy, and oz minus cz. And so let's create a new vector now that will hold this subtraction and simplify things a little bit. Now, I'm not sure why, but if you read the literature on ray tracing and most books, this vector that we're about to create has a name called L. So they use the alphabet letter capital L for denoting this subtraction of these vectors. I'm not sure why they picked L, but maybe you could think of it as a location of the new sphere in terms of the ray. So if we move around the sphere's center, then that'll relate back to the ray differently, and the L vector will hold that information. So it'll hold the offset of the sphere center from the ray origin. So let's combine these two first, ox and cx. And we're going to do a simple subtraction because it's ox minus cx. I'll use the blue color here to denote the new vector. So Lx equals ox minus cx. And likewise, we can do the same for the y components. Ly equals oy minus cy. And finally, Lz equals oz minus cz. And so I literally took the ox and cx and just moved them down here and placed them into a single number, a single part of this new vector that we made. I'm going to shrink these down just a little bit. And I'm just going to make a note here. Let vector L equals the difference of point O of the ray and center point C of the sphere. So now that we've done this subtraction and stored it in a new variable, we can simply rewrite these brackets as Lx plus T dx. And then that'll make it just two terms inside the parentheses that we have to deal with when we're expanding these brackets. So let's go ahead and see how that looks now in its new form. We're going to replace the OX and the CX with LX. And then just go on in the equation. And so it says plus T dx. So I'm going to write that. Plus T dx. And all of that needs to be squared. And now we can just continue and do likewise for the y components and the z components. And hopefully this will look a little better. Ly, and then we're left with plus T dy. And that all squared. Plus Lz plus T dz, all squared. And now we can continue with the equation. It says minus r squared equals 0. Minus r squared equals 0. All right, so I don't know about you, but I'd rather see something like this than something like this. Because, like I said, we're going to have to square these brackets. And so that's going to mean Lx plus T dx times Lx plus T dx. So we're going to have to write that out twice and then do the FOIL method. So FOIL, first, outer, inner, last. And so we're going to have to do those for the x components, the y components, and the z components. So our equation is about to get much longer. So now that we've simplified this equation a little, it's time to expand those brackets. So all these squared exponents here need to be expanded. And so let's go ahead and write that out. So when you say Lx plus T dx squared, that's just saying Lx plus T dx times Lx plus T dx. So we're going to write it out in expanded form. Lx plus T dx times the same thing. And now we have to do that for the y and then the z. So this is going to get quite long here. So we keep the plus sign right here. Plus Ly plus T dy times another Ly plus T dy. Plus, keep the plus sign from here. And then got one more to go. Do the z components. Times another one of those. I almost made it. I'm going to shrink this down just a little bit so it can fit on one line. And now we just continue with minus r squared equals 0. Okay, so getting longer. It's not at the maximum yet. That's the next line. But at least we have these expanded out so there's no more brackets that are squared. Now we have to distribute these terms. So when you have two sets of parentheses with terms in them that you need to multiply together, you can do what's called the FOIL method. And the FOIL method, which is FOIL, stands for first terms, outer terms, inner terms, and last terms. So that means we're going to do first terms, this Lx times Lx, plus outer terms, so Lx times T dx, plus the inner terms, which is T dx times Lx, and then finally plus the last terms is T dx times T dx. So this line I'm about to write is the longest one. So we're going to do first, so Lx times Lx is Lx squared. And now we have to do the outer and the inner terms. But notice that they're actually the same. So the outer is Lx times T dx. And if you do the inner, and if you go from right to left, it's Lx times T dx. So that's the exact same thing. So in other words, we have two of those. And we can simplify this by just saying two of those terms. So we're going to do two Lx T dx's. So keep the plus sign and then write a 2 Lx T dx. And now all we have to do is the last terms. So that's T dx times T dx. And we could just do T dx squared, but I'm going to separate the terms and do T squared times dx squared. And so that'll allow us to pull the T out eventually when we get to the bottom. So keep the plus sign. So T times T is T squared times dx times dx, which is dx squared. And even though these are stuck together, I put the squared exponent on the t as well as the squared exponent on the dx. So that way we can eventually pull this t squared out from this term. Now, just like we did these, we have to distribute the y terms and all the z terms too. So let's do that now. But the good news is it's all the same. It's just tedious. There's a lot of repetition in this equation. So it's not that hard mathematically. It's just that there's a lot of terms. So now we keep the plus sign, and now it's time for the y components. And we'll do something very similar to this. We'll just change the x's to y's. In fact, I'm just going to copy and paste it over here. And I'll make this a little smaller. Okay, and before we forget, let's change all the x's to y's and then all the x's to z's over here. So, and this one becomes z. And then finally, we add the minus r squared equals 0 at the end. Whew, oh boy, that was long. So this is the longest line that we'll have on this page. That's the good news. So let's read this from left to right and make sure we did everything correctly, because I was copying and pasting and sometimes errors can creep in. So when we multiply these two brackets together, we have lx squared plus 2 of the lx t dx's plus t squared dx squared. And then we do the same for the y, so L plus ly squared plus 2 of the ly t dy's plus t squared dy squared plus, and then we do the z components, so lz squared plus 2 of the lz t dz's plus t squared dz squared minus r squared equals 0. All right, and so let's make this look a little more clean and group all the like terms together in the same area of the equation so that all the squared terms, for instance, are together in the same part of the equation. And that'll lead to more simplifications that we can make. So we're just going to rearrange these terms in a different order. Let's put all the t squared terms first. So we have the t squared dx squared, and then we have the t squared dy squared, and then we have the t squared dz squared. Let's write those first. So now we've grouped all the t squared and the d squareds together. Next, let's gather all the terms that have a 2 on them. So we have 2 lx t dx, we have a 2 ly t dy, and we have a 2 lz t dz. And what do we have left? Let's see. We haven't done the lx squared yet, so let's put all those together that are like. So lx squared plus ly squared plus lz squared. So let's do those next. And I believe with that, we got everything over here, and then we just need to finish with the minus r squared equals 0, and we're done. Or at least for now. So minus r squared equals 0. So hopefully that looks a little more organized. And now that it's grouped in this manner, we can start to see some patterns and maybe pull out some things that can be factors. So notice that all these terms have t squared as a multiple. So we can actually factor out the t squared and just pull that out and then put the rest inside parentheses and then have the t squared on the outside of the parentheses. And then it's kind of like it distributes across those terms. So we're doing it in reverse. So let's pull the t squared out and then write the parentheses first. And we're going to put everything that's not a t in here. So dx squared plus dy squared plus dz squared. And all that goes in its own set of parentheses, and that's all multiplied with 1t squared. So the t squared will distribute across all those. So let's put that next, t squared. So that looks a little better now. We only have one t squared to worry about, and then we have a nice group of like variables here. And we'll take a look at that in a minute and see what that means. So now let's do the same with everything that has a 2 on it. So this one has a 2 stuck to it, this one has a 2 stuck to it, and this one has a 2 stuck to it. And so since they're all multiples of 2, we can pull that 2 out. And also, take a look at this. There's a t in here, a t in here, and a t in here. So that's a common factor also, so we can pull the t out as well. And so on the outside of the parentheses, we can have 2 on one side and then t on the other. So let's keep the plus sign. You have to always remember to keep the plus sign that's right here. And now we're going to pull out the 2. So write a big 2, parentheses, and then what's left? So we have Lx dx, Ly dy, Lz dz. And I'm not getting the t's yet, so we're going to put the t's on the other side of the parentheses. So I'm just getting the Lx dx plus Ly dy plus Lz dz. So let's write that. And everything is multiplied by these single t's. They're not t squareds, they're just t. And so let's multiply everything that we just did by t. I did it this way because we can see that the t can be by itself. So we're eventually going to try to pull out those t's. So we're going to have the t squared over here and then a t over here. So that's why I kind of separated the 2 on one side and then the t on the other. But it's the same thing. You could have done 2t or t2. It doesn't matter because they're all multiplied anyway. And then this part right here can't really be factored out because there's no common factor between all those terms. And then we have to stick on that as well. So let's just rewrite this section right here and just copy it and move it down here. So remember to keep the plus sign, so plus, and then I'm just going to rewrite it. So, okay, so now you can see it's beginning to take shape. So it's coming into a form now where we can make some simplifications in the notation, because if you notice, this right here, dx squared plus dy squared plus dz squared, where have we seen that before? And once again, the dot product of a vector with itself shows up in this unlikely place. So this is the same thing as saying dx times dx plus dy times dy plus dz times dz. And that's the very definition of a dot product of a vector with itself. And so we can rewrite this now as vector d dot vector d, and then put t squared against that. Now let's take a look at the next set of terms. So what do we notice about this group here? We have Lx times dx plus Ly times dy plus Lz times dz. Well, that's the very definition of a dot product between two vectors. So you take their x components, multiply them, you take their y components, multiply them, you take their z components, multiply them, and then add them all up and you get a simple number back. So this is like saying L dot D, or vector L dotted with vector D. And so let's rewrite that. And don't forget the 2. We need this 2 here because it needs to be whatever we get out of this dot product, we need to multiply by 2. And so we're keeping the 2. That's going on the outside. And then parentheses L dot D. So let's write that. Vector L dot vector D. And that whole thing is multiplied by a single t value. So now you can read this as d dot d times t squared plus 2l dot d times t. And now finally we get to this, the blue part here, lx squared plus ly squared plus lz squared. And where have we seen that before? Yet again, the dot product of a vector with itself shows up. So this equals L dot L, L times itself. So we saw the same thing over here. So dx squared plus dy squared plus dz squared equals d dot d. And we could do the same for the blue vector here. So let's keep the plus sign that comes from right here. So plus, and then we're going to do vector L dotted with itself. And now we just have the minus r squared to go and we're done. So if you worked with these type of equations before, you may instantly recognize this. But since we have these dotted vectors here, it might be obscuring the fact that it's a very famous equation. And so take a look at the t variables in particular. So we have t squared, and we have a t, and then we have a constant equals 0. And so that hopefully will be familiar. And let's simplify it even further, and then you'll really see what it is. Remember that taking a dot product between two vectors, or a vector in itself, gives you back a simple number, a constant. So let's draw a little purple underline here, squiggly underline, and we're going to call this constant a. Now, if you just look at this portion, 2 times the dot product of vectors L and D, that also gives you back a number. So let's call that another constant, and that we'll call b. And then finally, L dot L gives you back a number minus r squared. That all gives you back a number. So that could be considered a constant also. So let's call that whole thing letter C. And now let's rewrite it in its final form. And hopefully you'll see what this becomes after all this math. So I'm going to use the new names that we gave these constants. So a t squared plus b t plus c equals 0. And finally, after all this work, we arrive at our final destination, and hopefully this looks familiar. This is called a quadratic equation in T. So the unknown variables are t, and we have a t squared and a single t over here. And the t squared is multiplied with a constant that we named a. And then the singular t is multiplied by another constant that we call b. And then you add on a third constant called c, which has no t on it. And all that should equal 0 if you find the correct t values. And if you've had quadratic equations before in your math class, you may recall that there are indeed 2 solutions for the t values that will work on these equations. So you can plug in one t into this equation and it'll equal 0. And there'll be another value of t that you can plug in and it will also equal 0. So, and we'll get to that, how we're going to find that in just a moment. Let's write out what a, b, and c are, just to be clear. So a here is representing d dot d. So we're going to write that out. And then we said that b was equal to 2l dot d. And finally, c equals the rest. So L dot L minus R squared. And I'll put a light blue box around this equation. And this equation in the blue box is called a quadratic equation. So let's go back to the top. And so where we started was we had two different equations that don't seemingly go together. We have one implicit and one explicit. But by using the clever rules of algebra and combining those two equations, we were able to eventually isolate t on one side of the equation and make the equation in terms of t. Now our final equation does have a t squared and also a single t, but this form of having a constant times t squared plus another constant times t plus another constant equals 0 is a very standard equation, and that's called a quadratic equation. And the word quadratic comes from the fact that we have the t value squared here, and so it's of degree 2. Remember how we talked about different degrees of polynomials. So if you have no exponents in your equation, that's a linear equation, like we saw with the plane on the last episode. But now we have this new equation that has a t squared, so now we must say it's a quadratic equation. So now the question remains, how do we find the t values? Because remember, we need t0 and t1, so we need two different t values. Well, luckily for us, very smart mathematicians long ago, possibly thousands of years ago, figured out that you can solve for a t in this instance, even if it's squared, by using the quadratic formula. And so on the next slide, let's take a look at the famous quadratic formula, which you might have encountered in math class in the past, and see how we can use that quadratic formula to solve for t in this quadratic equation. Okay, so let's take a look at the quadratic formula. And this is the last whiteboard, I promise. So if we've been given a quadratic equation, like this one here, at squared plus bt plus c equals 0, you can use the quadratic formula to solve for t. And just in case you don't remember how the quadratic formula is defined, I've written it out here. It says that t, which we are looking for, is equal to negative b plus or minus the square root of b squared minus 4ac, and then all of that is divided by 2a. And most equations that you'll see don't have this plus and minus stacked on top of each other like this, but what that means is that you could either add this part here or you could subtract this part. So if you add this part, then that'll give you a solution for t. And if you subtract this part, that'll give you another valid solution for t, but it'll be a different solution. And so the plus minus means that there are two solutions for t that exist. So how does that relate back to what we were trying to get with the t0 and t1 parameters for our array that's intersecting a sphere? So if I copy this entire equation and I use the minus sign only, and then copy the entire equation again and use the plus sign only, then I'll get two unique solutions for t. And so here I've just copied the whole equation down here and I copied it again over here, but you'll notice that instead of a plus minus, I have the minus for this solution, and then I have the plus over here for this solution. That's the only difference between these two. So when you read this entire equation, that's what that plus minus means. You could go either way. You could go the plus route or the minus route to get your two t values that you're interested in. And so the t0 value, the first value, is always the lesser of the two. And so we use the minus sign on this version of the equation. And then the t1 is always supposed to be greater, so we use the plus sign for the addition route of that equation. Now, there's a special part to this equation, and that's the terms underneath the radical sign or underneath the square root sign. And so we have b squared minus 4ac. So in math, that is called the discriminant. So the b squared minus 4ac above, this part right here, is called the discriminant. And this is important to know because we can test early if there is a solution to this quadratic equation. So when we put these equations into the code, we're going to first check this little part here, this b squared minus 4ac, and if that part, that discriminant, this part right here, is positive, if it's greater than 0, then two solutions exist. And it'll give us back t0 and t1, and that's what we wanted. However, if the discriminant, this part right here again, is negative, less than 0, then no solutions exist. And that's because you can't take a square root of a negative number. Now, I realize that you can do the square root of -1 is I if you consider complex numbers. But in ray tracing and in general ray casting of quadratic shapes like this, where we have to find a solution to a quadratic equation, we're only interested in real numbers. So real numbers that are on the number line. And so if this discriminant here turns out to be negative, we can immediately exit from the function and have an early out because we know that there's no solution to the square root of a negative number. It doesn't make sense when you're talking about real numbers. However, if it's positive, then we can definitely take the square root of any positive number, and therefore two solutions do exist. And if we take the minus route, we'll get t0, and if we take the plus route, we'll get t1 back. And so after all this math we've done and all this hard work, we're finally ready to add our ray versus sphere intersection routines to our JavaScript library. And so even though it took a whole lot of exposition and math to get to this final result of a quadratic equation, by the time we get to the code to actually implement this, it's just going to be a handful of lines of code. And so the quadratic formula itself will be maybe 10 lines or so. And the quadratic formula needs the quadratic equation, which has the a, b, and c constants. And so all we have to do before we use the quadratic formula is just to compute these simple constants here, this a, b, and c. And so inside of our actual ray versus sphere intersection function, we'll quickly compute these coefficients. So we'll just do d.d to get a, and then 2 times l.d to get b, and then l.l minus r squared to get c. And once we have a, b, and c, we can then call the quadratic formula function that we'll code up, and that will plug in the a and the b and the c for us, and then the computer will take those constants and perform these calculations with those constants that we provided in the purple color here. And if this section here turns out to be negative for any reason, then it'll come back early and say the ray has completely missed the sphere, so you might as well just exit early. And then if there is a positive discriminant underneath the square root sign, then it will go ahead and do both of these versions of the quadratic formula. So the one with the minus sign here, and then the one with the plus sign here. And that will give us the t0 and t1 values that we desire. And so even though this was a whole lot of math, when we implement it in the code as functions, then we can just call those functions and forget about it and let the computer do all the hard work. So computers love crunching numbers, and we're just going to let the computer do all the calculations of the constants and the quadratic formula. And so we'll just let the computer do all that in the background, and then we'll get to enjoy our newly rendered spheres in our scenes. So without further ado, let's head over into the code. All right, so now let's open up Visual Studio Code. And we were just in this file a moment ago, and this is actually the file that we want to work on first. So we're inside the mathutils.js file. And that's our JavaScript library that does all the vector and math operations. Okay, so scroll down to the bottom. And the first thing we'll add is the famous quadratic formula that will help us solve the quadratic equation that we handed. So real quick, let's go back and look at the quadratic formula and see what it needs to do its work. So we're going to give the quadratic formula a quadratic equation in this form. And so it's going to need these a, b, and c constants, or coefficients if you like. And then once it has those, it will be able to do its work and return a t0 and t1 value back to us. So when we design this function in our code, it should take 3 parameters, a, b, and c. And also we probably want to save this special part right here called the discriminant. So let's create a variable that will hold this result right here, and we'll be able to tell from the discriminant if it's positive, then there is a solution, so we should continue. But if it's negative, then there's no solution, and so we should exit early. So let's go back into the code and go down here on the bottom line and hit enter a couple of times. So I'm just going to create a couple of variables. What we're wanting from this function is t0 and t1. And so we haven't added those to our programs yet. So let's add those now. Let t0 equals 0, and we can just initialize it to 0. And then let t1 equals 0 also. So these variables will be what is handed back to us from the quadratic formula if 2 solutions exist. And next, let's create a variable called the discriminant, and that will hold the part under the square root sign or the radical sign. So let discriminant, and then we can set that to 0 also. And notice that we have to divide by 2a twice, possibly. So let's save this 2a in a variable. And in general, when you're dealing with computers and math, it's better to multiply than it is to divide. The multiplication on a computer is slightly faster than the division, even on today's modern machines, which are blazingly fast. But you have to remember that we're doing this operation possibly millions of times per second. We're sending out a ray through each pixel, and there could be millions of pixels on the screen. And for each one of those rays, we're going to be doing the quadratic formula, and that's just for one shape. If we have multiple spheres in our scene, we're going to have to do the quadratic formula times how many objects we have. So when you're talking about doing this operation several million times a second, then it makes sense to optimize little operations like this, like multiplication versus division. And so let's save this variable as not 2a, but instead 1 over 2a. Because if we just save it as 2a, we'll have to divide by that 2a. But if we save it as 1 over 2a, we can multiply it by that. We'll see that when we get to that part in the code. But for now, I'm just going to create a variable that will hold that 1 over 2a for us. So let's call it 1 over, and then maybe an underscore here, and then 2a. And so hopefully that'll be clear to anyone looking at your code, or you yourself looking at the code after a long time of not looking at it. And so it's 1 over, and then this is kind of like a fraction or a division sign, and then 2a is on the bottom. 2a is the denominator. And we can go ahead and initialize this to 0 also. And now we're ready to implement the quadratic formula function. So let's go on the next line, maybe hit enter one more time. And I'm going to scroll up a little bit so we can see better. So this is the quadratic formula. but instead of calling the function quadratic formula, let's call it solveQuadratic because it's solving a quadratic equation. And so I think that name for the function represents more of the action that we want it to do for us. So it's solving a quadratic equation and it's handing back the roots or the t values that we want. And remember in JavaScript, we do function keyword solve quadratic. And recall that it's going to take those 3 coefficient variables as inputs. So it needs 3 parameters inside these parentheses. And so we can just simply call those A, B, and C. And then hit enter to go on to the next line. And opening curly brace, and it'll close it for you, and then hit enter. So let's go back to our slide on the quadratic formula and just recall what we need to do. So remember I said that we could do an early out. So if this part right here, the discriminant, is negative, we can exit this function early and be a little quicker. And so let's first calculate this discriminant right here. The discriminant is equal to b squared minus 4ac. And so let's put that in the code now. So the discriminant, and you can hit enter, it'll pop up there, equals. Now when coding a squared exponent, you just simply multiply b times itself. So let's put that in parentheses. So b times b. And then we need minus 4 times a times c. And we'll put the minus sign here, and then let's create another set of parentheses. 4 times a times c. End it with a semicolon. And these parentheses are not necessary, but I just wanted to make sure that the multiplication gets done first and then the subtraction gets done last. And so that's the case here. We're going to do the b squared first, b times b, and then the 4 times a times c next, and then we will subtract that from this result here. And now we should have the discriminant. And we had said that if the discriminant is negative, we should exit early. So let's put a check in for that now. If, and then opening parenthesis, and I'll close it for you, and then discriminant is less than 0. And go on the next line and opening curly brace, and it'll close it for you. Now hit enter, and we're going to return early. So instead of just returning, I want to return some kind of value that we can test against when we're inside the Hooray intersectSphere function. So instead of just returning, let's return false. And so that'll return a false value, and we can check for that later on when we're doing the actual Hooray intersecting sphere function. So return false. So this means that there was no real solution to this quadratic equation. And remember that we had said that in that case, that means the ray is not hitting the sphere ever, and so it's not even pointing towards the sphere at all. Now hit enter, and let's take a quick look at our quadratic formula. So now if we determine that this is positive and that there is a solution to this quadratic equation, then we can go ahead and compute this square root. So let's do the square root of the discriminant. And we can just reuse the variable name now that we know that there are 2 solutions to this quadratic formula. So discriminant equals, let's call the square root function, and that is accessed through the JavaScript's math object. And so capital M math dot square root, so SQRT, and it'll pop up here. You can click there, and that is a function itself. So it needs parentheses. So open parenthesis, and it says it needs a number inside there to do the square root on. And so now we want the discriminant to be underneath the radical sign. So we're essentially setting the discriminant to the square root of itself. So let's type discriminant again, and then semicolon. So this will perform the square root function on the discriminant and then save that back into the discriminant itself. So now discriminant is updated with the square root of itself. Now we can use this 1 over 2a and store that result in this variable. So let's go on the next line, and 1 over 2a equals 1 over, so 1 divided by, and let's do an opening parenthesis here, and we're going to put inside the parentheses 2 times a. So 2 times a, and the semicolon. And so now 1 over 2a is 1 over 2a, or 1 divided by 2 times a. And so this will compute this only once for our function here, and then we can reuse this a couple of times and multiply by it instead of divide by that 2a. And hit enter. And now let's go back and check the quadratic formula. And so the quadratic formula states that in order to get t0, we need negative b minus the discriminant. So remember, now we have the discriminant as the square root of all that. So we already have that saved, and we already have this saved as well. So let's type in negative b minus, and then the discriminant, and then multiply it by 1 over 2a, and that should do it. That should give us this t0 value. So our t0 that we're wanting is equal to, oh, and let's put this in parentheses. So opening parenthesis, and then negative b minus discriminant times 1 over 2a, and semicolon. So this set of parentheses just ensures that we do the negative b minus the discriminant first, and then divide that by 2a, or multiply by 1 over 2a, which is the same thing, but a little faster on the computer. And so now we've successfully done this section here, and then all we need to do is do it with the plus symbol, and we'll get the t1 value as well. So let's do that on the next line. So hit enter, and now we have t1 equals, and this is going to look very similar. In fact, let's just copy this whole thing, Control C, Control V, and all you have to do is change the minus to a plus. So we add the discriminant instead of subtracting. Now we can read this as t1 equals negative b plus the discriminant times 1 over 2a, which is the same thing as divided by 2a. And so this is the subtraction version of the equation, and then this is the addition version of the equation. So now we have both the subtraction version here and the addition version there. And so we should have our t0 and t1 values. And that's it for solve quadratic. So it's pretty easy. And there's one last thing to do. We need to return a success value. So remember here that we returned false, meaning that there was no solutions. But now, once we get past this point, and if the discriminant is positive or above 0, we know that we're going to get two real solutions, which are t0 and t1. So we want to report back to the calling function that we succeeded. And so instead of just typing return, let's return true. And that'll return a success value. So let's go on to the next line and type return true. So later on, when we're in our ray intersecting sphere function that calls out to this solveQuadratic function, then we can easily test if it's false, then we should just stop the ray versus sphere intersection altogether and then go back to the main program. But if it returns true, then we know that there are two real solutions to the quadratic formula, and we can go ahead and render the sphere using the t0 and t1 values that we get back from this formula. So now let's implement our ray intersecting sphere function. And just to remind ourselves what we're trying to do, let's go back to the slide about the ray versus sphere. So our ray intersect sphere function will need to compute these coefficients. So the ones in purple here, we need the A and the B and the C coefficients that we can feed into the quadratic formula, and then it can do its work and then spit back out the t0 and t1 values that we're wanting. But before that, we actually need a new vector called L. And remember, we created this vector up here, and we said let L equals the difference of the ray origin and the center of the sphere. The vector L holds the difference between all the components of the ray origin and the sphere center. And if you look at this, it's OX minus CX, OY minus CY, OZ minus CZ. Well, in vector terms, that's just a simple vector subtraction. And the good news is we already have that in our vector libraries. So we can simply create a new vector called L and then set it to the ray origin and then just subtract off the sphere center. And then we'll have the new sphere location in terms of the ray. So let's create a new vector 3 called L. So hit enter a couple of times, and I'm going to scroll up here. So let capital L equals, and then we're going to create a new vector 3. So new vector 3, and it should pop up here because it recognizes that. And then this is a constructor function, so it needs parentheses, so opening parenthesis. And then it reminds us it needs an X, Y, and a Z. But actually for this particular vector, we don't need to initialize it right now because it's going to get calculated in a moment anyway. So we can just leave these parentheses blank and then end it with a semicolon. And now we're going to need those constants. Remember the A, the B, and the C constants, or coefficients if you like. So let's create variables for A, B, and C. Let A, and in JavaScript, you can declare multiple variables at the same time on the same line. So the way you do that is just separate them with commas. So let A, comma, B, comma, C equals 0. And then hit enter, and hit enter one more time maybe. And then we have to name our function now. So this is the function that will actually compute the intersection of a ray and a sphere. And so let's go back to our ray versus plane function and see what we called that. So we had called that intersect plane. So I'm inclined to keep with that naming convention and just call it intersect sphere. So let's do that to be consistent. We declare a function by using the function keyword. So function intersect, and plane comes up here, but we don't want that. We want sphere. And then opening parentheses, because all functions need parentheses. So opening parenthesis. And let's recall what the intersect plane function took as parameters. So it took the plane origin, the plane normal, because that's how we define a plane. And then it took the ray origin and ray direction. So we will definitely need these two, ray origin and ray direction. But instead of these, let's do the sphere position here, which is that C point, that center point of the sphere. And instead of the normal, let's do the sphere radius. And so this new function will have all it needs to work. So let's name the first parameter sphere position, comma, and then sphere radius, comma, and then our ray origin, and those should pop up. So ray origin, comma, ray direction. And then hit enter, and opening curly brace, it'll close it for you, and then hit enter. And I forgot to mention this on the last function that we did, but these appear gray until you actually use them inside the function. So that's a nice little VS Code feature that will tell you if you've used all your parameters or not. But hopefully all these will turn white as we start using them inside this function. So I'm going to scroll up a little bit. And so the thing we want to do first, going back to our math page here, is we need to set the L vector to the O vector and then subtract off the C vector. This O vector, this OX belongs to this O vector here, so it's the ray origin and then the sphere position or the center point. And so let's set L to the ray origin first. We'll just copy it, and then we'll subtract off the sphere position or the center of the sphere. So let's try that now. So vector L, capital L, dot, copy, and it reminds you that's a method, and then when you type the opening parenthesis, it reminds you it takes another vector inside the parentheses. So what vector do you want to copy? And so we want to copy the ray origin. That was the O vector on our slides a moment ago. So ray origin. And now notice, see, it highlighted that ray origin. So we've successfully used this one. We have 3 more to go. End that with a semicolon, hit enter. And now we can subtract off that sphere center or the sphere position that we named it. So let's do L again, and then this time dot subtract, and opening parenthesis, and it says once more that we need another vector inside the parentheses, and so we're going to subtract off the sphere position that we were handed. So sphere position. And then that one lights up. And now a semicolon and hit enter. And now back on our slide here, once we have that L vector that contains the newly calculated location of the sphere in terms of the ray origin, we don't have to do any of this math. So all that was just to show where these equations come from. And so the good news is that we just need to compute these little coefficients, the A, B, and C. And we have the formulas for those right here. And so they're just the simple dot products. And so A is equal to vector D dot vector D. And so we'll do that first. So the coefficient A, and this is up here, remember we declared A, B, and C to use. So A equals, and the vector, and just to keep this on one page, I had just used single letters for these vectors, but this D means the ray direction. So remember that the ray origin was in this pink color, this O, and then the sphere was the purple one, the capital C, and then the ray direction was this yellow D here. And so we're going to do ray direction dot ray direction. And so let's do that now. So ray direction, and that's a vector, and now we can call its dot function. So dot, and then the word dot, and now opening parenthesis, and we're going to type in ray direction again. So it's ray direction dot ray direction, or a vector dotted with itself, as we discussed earlier today. So ray direction, and that with a semicolon. Now we have A, so there's two more to go, so we need B and C now. So let's go on to the next line, and B is equal to, and let's go back to our whiteboard here and see what that was. B equals 2 times L dot D. So the L vector dotted with the ray direction. And then we multiply that by 2. So B equals 2 times the L vector, so capital L dot, and then the word dot, and then opening parenthesis, and the other vector will be the ray direction vector. So ray direction. And that's it for the B, so we end that with a semicolon. And now C is the last one remaining, so we do C equals, and what was that? C was L dot L, and then minus R squared, or the sphere radius times the sphere radius. So let's try that now. L dot, and then the word dot, and then the L vector again inside the parentheses. So L dotted with itself, minus, and now we need the sphere radius squared. And so remember how we do that in code is usually just do sphere radius times sphere radius. And see, that's the only one that's grayed out right here. We haven't used that yet, but now we're about to use it. So, and let's go ahead and put this in its own set of parentheses so that we make sure it gets done first before it does the subtraction. So let's do opening parenthesis and type sphere radius times sphere radius. And now hit semicolon. And that should be it for C. So we have L dot L minus sphere radius squared, or sphere radius times sphere radius. And that should be what this is saying here, L dot L minus sphere radius squared. And so with that, we've completed all these coefficients. So we have the A, the B, and the C values all calculated now. And at this point, we can hand those coefficients into the quadratic formula function that we just created. So let's do that now. So go on the next line. Now remember, when we call this solveQuadratic function, it's going to return either false or true. And so when we call this function inside this intersectSphere function, we should check if it's true or false first. And that way, if it's false, we can exit early out of this function as well and be done with everything. So let's check if it's false first, and then we can exit early. And then if it's true, it'll just go on and keep doing this function here, this intersectSphere function. We're going to do a check, and that's an if statement. So if, opening parenthesis, and now we're going to call the solveQuadratic function inside the if statement. So solveQuadratic, and you can click here, it should pop up. And that's a function, so it needs its own set of parentheses. So opening parenthesis, and it'll remind us that we need to supply an A and a B and a C coefficient as parameters. And luckily we've just done that, so we just computed A, B, and C. So we can simply type A, comma, B, comma, C. And we want to check if this function returns false first. So let's click inside these two ending parentheses and push a space. And now we're going to see if it's false. So do a double equals. And remember, in JavaScript, that's how we check if something is equal to something. You can't just put a single equals, you have to put double equals. So double equals false, because we want to check first if it returns false for any reason. And now Let's go on to the next line and hit open curly brace and enter. So if it comes back false, what do we want to do? Well, we want to exit this function, of course, but instead of just returning, let's return infinity. That means the t value for this ray versus the sphere that we were testing is infinite. So it will never hit. If you extend the ray out for infinity, it'll never hit the sphere. And so back in the ray tracer, when we call this function, if we get infinity back, then we know that it didn't hit the sphere at all, and we should just draw the sky or whatever's behind the sphere. So return infinity, and it's a capital I in JavaScript. And that was a statement, so semicolon. Now recall, the whole point of this intersectSphere function is to return back a t value for the ray. But as it is now, the solveQuadratic function will set t0 and t1. But we just want the best t value. We don't care that there's a t0 and a t1. We just want the nearest t. So remember up here that we had set t0 and t1 in the solveQuadratic function. And now we need to kind of sort those out and see which one is the best one to use. And so let's go on to the next line here below this curly brace. Let's first test for the t0 value, because if that's positive, so this one right here, this t0, if that's positive, then that's always going to be the one that we want, because t0 is always the closest t, or the lesser of the two, between t0 and t1. If, opening parenthesis, and then t0 is greater than 0, because remember, to be a valid value for t, it has to be greater than 0, and it has to be less than infinity. If it's infinity, that means it didn't hit anything, and if it's greater than 0, that means it's in front of us. But if it's negative, then that means it's behind us, and we shouldn't use that t value at all. So if t0 is greater than 0, or it's positive, then go on to the next line and opening curly brace. And now we can return the winning t value. So return t0, and then a semicolon at the end of that line. But what happens if t0 is negative or less than 0? Well, we have to move on to the next one and try the next one. So let's try t1 in the same manner. Go on to the next line. If, and we can actually do an else if here. So else if, opening parenthesis, t1 is greater than 0. And then go on to the next line, opening curly brace, enter. I'm going to move up just a little bit. So if t1 is greater than 0, then that's a good t value as well. So we want to return that. So return t1 and semicolon. But what happens if none of those are valid? So let's say t0 is less than 0, so it falls through here, now goes to here and it checks t1. Let's say t1 is less than 0. It's negative also, so we have to go down now and return no intersection. And the way we do that in this function is just returning infinity like we did up here. So if the quadratic formula fails, then we just return early with infinity. So the ray will go for infinity and it'll never hit the sphere. If we find a success with t0 or t1, then we return those as our t value for the ray that we're looking for. And if both of those are negative, so they're both behind us, and remember, we don't care anything about the intersection points behind the camera or behind our rays, then we should return infinity again, because we'll never hit the sphere. So we can come down here and go on to the next line, and in this case, we're just going to return infinity. So return capital I infinity, and semicolon to end that statement. Okay, and that's all the functions that we needed to do today. It really wasn't that bad, was it? So even though we had a lot of math, like this whole page of the quadratic formula, and then we had this whole page of math here to get to the quadratic equation. When we boil it down and we get to the code, it's only about 15 lines of code. So now comes the fun part. Now that we've done all this infrastructure, we can have fun by adding a sphere to our scene. So we can define a sphere with a radius and a position in the world and see if this function truly works and render a sphere in the scene with our ground plane and our gradient sky. All right, so what do you say we make a new demo that shows off our new ability to intersect rays with a sphere? So go into intersectPlane.html, the file that we had created on the last episode. And with that clicked, here you can see it highlighted in our file view. Let's create a new HTML file that will hold our new demo that intersects rays with a sphere. So if you go up to here, it'll appear when you hover your mouse close here. So new file, it's this little icon with a plus on it. So click that. And let's call this something similar to what we named the other demo last time. So we'll just name this intersectSphere. So intersectSphere. .html. And then you'll see the opening and closing angle brackets pop up here, which tells you it recognizes that file extension. And then hit enter. And now that'll create a new HTML file called intersectSphere. Now just quickly go back to intersectPlane.html and select all that code and Control C. And now go back into intersectSphere and Control V. And before we go any further, let's change the title so we don't get confused. So change plane to sphere. And in a moment, we'll come back and update this file path because right now it's going to intersect plane. And speaking of that, let's go to intersectPlane.js, the one we did last time. And with that selected, intersect plane, let's create a new file in this JS file folder. So just make sure you can either click here or here. So if you click intersectPlane.js, that makes sure that you're in the right folder here. So we want it to be in the JS folder before you create a new file. So now go up to the file icon, and it's the little file with the plus symbol, and then click new file. We'll name this the same thing as intersectSphere.html, but we'll use a .js extension instead. So intersectSphere dot, and then this time we want JS. And then you'll see this little JS symbol pop up here, and that tells you that it recognizes that file extension. And so hit enter. And now once more, go back to intersectPlane.js and go up here where it says selection, select all. And that'll select all the codes so you don't have to drag your mouse up and down. And then Control C. Now go back into our new file, intersectSphere.js, and Control V. So that should paste in all the code. And now we should have a working demo for our new intersectSphere demo, although it's not going to do anything different from what we had last time, obviously. But let's go ahead and check that everything's working. Oh, and there's one more thing we need to do. We need to go to intersectSphere.html and update this file path, because right now it's pointing at the wrong file. It's going to intersect plane. So now we want it to go to intersectSphere instead. So just go right here and erase the text up to JS. And then we get to see one of my favorite features of VS Code. So we type /, and I just never get tired of this. And so we select intersectSphere.js. And now the file path is correct. So it'll be able to find this intersectSphere.js that we've just created. And with this file in view, let's go ahead and open up our live server and see if everything's working. And like I said, it won't do anything different. It'll just have the ground plane and the sky in the background like we did last time. So it's very tiny. It's on the bottom right here. Click on Go Live. And that should open up your default browser. Something's not working. So I'm glad this happened on camera so I can show you a little debugging session here. So obviously we expected to see our ground plane and our sky that we had working last time. And now we go to run this new demo, which was just an exact copy of the old demo, but it's not working and it's giving us a blank screen. So there must be an error somewhere. So anytime that happens, you can right click. So right click and then inspect. And you'll see here this red X, it has errors. And so we must have forgotten about something or messed up something. So let's click on console. And I'm going to pull this up just a little bit. So it says identifier B has already been declared. So now let's head back into the code and see if we can find where B has already been declared. I don't remember that, but so let's head into intersectSphere and see if we've already declared B. Oh, look at that. There it is. So we had this old RGB thing, and I don't even think we use this anymore. Let's check R, G, and B. And that was for the R, G, and B channels for the color. Yeah, because this right here is our own text that we had built up from scratch. And then we fill in the rectangle with that color that we built up from the text. So we no longer use the variables R, G, and B. We had those a long time ago when we started. We were experimenting with different colors and random colors and all that kind of stuff. And so I just forgotten to take these out. So let's take out let R all the way down to let B. So those three lines can be safely removed. We will not need those. So let's delete those. Okay, and now let's go back into our demo and see if it complains anymore. Hey, all right, it works. So I'm gonna get rid of the console here and it should re-render. All right, awesome. So we're back to parity. So now we got everything working and we're ready to add our new sphere shape to our scene. Oh, and before we do that, let's click out of intersectPlane.html. So click X and click out of intersectPlane.js. So X that out as well. That's so we don't get confused and accidentally update the wrong file when we're trying to work with these two files here, because the code kind of looks similar since we copied and pasted everything. Now, before we add our spheres, there's one small thing I would like to change, and that is the gradient sky. In preparing for this video, I realized that there's a slightly better way to handle the gradient color versus the fog in the background. And so let's just update some of these variables and change a couple of lines here and there and just make the sky and the fog system a little more flexible. But this won't take long at all. So go under where it says fog color and hit enter. And I'm just going to add a new color, which is a vector 3. So let's call this gradient sky color equals new vector 3. And remember, all colors are also vector 3s, just like the arrows and just like positions. And then this is a constructor function, so it needs parentheses, so opening parenthesis. And actually this gradient sky color will be computed later. And so even though it says we need an X, Y, and Z, it'll just default to zeros for those if we leave this blank. So just type semicolon at the end. and we'll compute that later. So now at this point you should have 4 colors here. So we have a sky color that's like a bright blue color, and then we have a ground color which is a medium green, and then we have a fog color which is a light gray color, and now we have this new gradient sky color, and that's going to transition from the fog up to the top of the sky, which is this color right here, this sky color. So it should go from like a grayish color to a deep blue as you get higher in the sky. So now scroll down to where it says ray direction.normalize, and then go underneath that. And all we're going to do is select this line right here and then just paste it up here and use the gradient sky color instead. So just select this line, the color vector.mix line, and then copy, and then paste it under this ray direction.normalize. And now erase color vector, and then instead let's use the gradient sky color that we just created. So gradient sky color, and it should pop up. So now as we loop over all these pixels, it'll go ahead and pre-compute the gradient sky color and then save it in this vector here, and then we can mix that with other things in the scene. And now just go right here and we can take out this commented line. And go right here where it says fog color and remove fog color, and instead type gradient sky color. So here's where we're going to use it. Gradient sky color. And then here now we can take out this line because we're doing it up above. So take out the color vector.mix line and go up one line here, and we can uncomment this. And now we want to copy the gradient sky color. So color vector.copy gradient sky color. Okay, so with those small changes made, let's go back into our demo and make sure everything's working. Yeah, so everything's working as expected. We have the ground plane receding into the fog, and then the atmosphere kind of blends from the fog color up into the bright blue color as you get higher and higher up in the sky. So that's all good now. All right, so now it's the moment we've been waiting for. It's time to define a new sphere for our scene, and we get to tell the program how big we want the sphere to be and where we want the sphere to be located inside the scene. So let's go back up to the top of this file. Go to the right of this plain normal.normalize line and hit enter a couple of times. And now let's define our sphere. So remember that you only need 2 bits of information for all spheres, and that's a radius, how big it is, and where it's located in the scene, so its position. And also we should give the sphere a color as well, just like we did for the ground color. Oh, and for this new sphere demo, let's make the ground a grayish color because we're going to color the sphere maybe like red, and red on green doesn't look that great when you put it all together, so red on a medium gray will look much cooler, I think. So let's go ahead and change the ground color to be gray instead of our grassy green color that we had. So go inside ground color and just erase all those numbers, and let's make it a medium gray. So that's all the same in each channel. So the red channel, the green channel, and the blue channel are all the same value. So let's do 0.5 for everything. 0.5, 0.5, and 0.5. And that should produce a nice gray color. And let's go back and look at that. Cool, okay. So now we have more of like a rock or a stone or concrete look. And we're going to place our sphere right on that ground plane there. And I think we'll start off with a red sphere, which will look nice against this background. So let's define our sphere now. So go right here below where it says plane normal. And let's start out with the radius of the sphere. So how big do we want it to be? So let sphere radius equals, and I'm going to give it an arbitrary size. So let's just do 3 for now and see how that looks. 3 units. And then type semicolon and then hit enter. And now we need to position the sphere in the scene. So let sphere position, and we were typing that a moment ago, so it recognizes that. Sphere position equals, now we have to set this up as a new vector. So a new vector 3, and we should go ahead and define it here. So where do we want the sphere to be positioned? For now, let's just have it right in the middle. So x will be 0, y will be 0, but we have to move it back a little bit, otherwise it's going to be right in our camera. And if you recall, the positive z direction comes out towards you, but the negative z goes back into the scene. So we want to push our sphere back into the scene. And so therefore it's going to need a negative z value. And so let's move it around 20 units back. So we're going to do negative 20, and that'll push it negative 20 away from the camera in the negative z direction. So just type zeros for the x and y, and we can fool with those later if we want to move it up or down or left or right. And then let's place it back in the scene a little bit. So negative 20 back, end up with the semicolon. And just like we did for the ground, let's give our sphere a color. So, and that's also a vector 3. So let sphere color equals new vector 3, opening parenthesis. And now we define the RGB channels for this color. And so, as I said a moment ago, I think I want to start out with a red sphere. So let's give it a full red channel and then maybe just a little bit of green and a little bit of blue. So 0.8 in the red channel, and then just a tad in the green and blue. So remember that we should avoid just leaving zeros in the other channels if we don't want those as a part of our color, because in the real world, you'll hardly ever see a pure red. It'll have some green in it and it'll have some blue in it, no matter how small, but it'll have a non-zero value for those. And so if we want our red sphere to look a little more like a real world red color, then we should add just a little taste of green and blue to it. So let's do 0.01 in the green channel and 0.01 in the blue channel. And so that'll just give it that little realistic touch, I think. And then end that with a semicolon. And now hit enter and go to where it says let t equal 0. So we are going to keep this in here, but now we need to add something to it, because recall that what we're trying to find when we raycast an object like a plane or a sphere is the closest t value. In the past, we only had one object. We had a ground plane and that's it. So if it hits the ground plane, great, you color it and you're done. If it doesn't hit the ground plane, you draw the sky background. And so that's very simple, but when you add more than one object, now they're all competing for that t value. So let's say you had a ground plane and then a sphere, and let's say the ray hit the sphere first, but you usually check the objects in an arbitrary order. So let's say you get back from the ray intersect function a t value, and then you go ahead and draw that, but then you raycast the plane and that happens to be behind the sphere, and it comes back with a valid t value. So you're like, oh great, I hit the plane, and then you draw the grass below it or the ground, but that's incorrect because now you're drawing the ground where the sphere should be, and so you won't see your sphere anymore. So in order to avoid mixing up the t values and drawing incorrect items that are further away than the closer ones that we want to see, we have to have a variable that will hold the nearest t value. So that's what we're going to call it. So let's call it nearestT. Go right below this let t equal 0 line and let nearest t, and I'll do capital T to distinguish these two t's here, equals 0, just to initialize it, and semicolon. So now we'll have a record of the winning t value or the nearest t value. And whatever object out in the scene reports back with this winning t value or this nearest t value, that's the object that we're going to draw. And we're going to disregard all the other intersections that we get back from the other objects. So now that we've added this nearest t variable, we can go inside the draw function, and this, recall, loops over all the pixels on the screen, and it sends out an array for each pixel. And so let's go down to where it says t equals intersect plane. And let's add our intersectSphere function now. And so we can just click right in here, and I'm going to move this over a little bit so we can see better. And then maybe hit enter one time. And let's do a similar function call here on this line. So just like we had t equals intersect plane with these parameters, let's do t equals intersectSphere. And so that way we can also check for the sphere. So now t equals intersect, and it should pop up here, intersectSphere. And that's also a function, so it needs parentheses, opening parenthesis, and it reminds us of what parameters it takes. So it needs the sphere position, it needs the radius, and then the ray origin and the ray direction. And the sphere position we defined earlier, so we can just type that in, sphere position, comma, sphere radius we also defined, sphere radius. I think we chose 3 for the radius, and then comma, and then the ray origin, and finally the ray direction. So ray origin and ray direction. And that was a statement, so we end that with a semicolon at the end of the line. Now maybe hit enter once so we can put a space between these two calls here. So if you look here, we have intersect plane, and then we get a t value back, and then we test that. If t is less than infinity, that means we got a good t value. But now we need to do slightly more work than that because we have multiple objects that are all competing for that t value. And so remember, we have to select the winning t value or the closest t value, and that's the one that always wins. So whoever has that gets to be the object that's rendered. And so we're going to do a slightly different kind of check. If our t value that we got back is less than nearest t, then go on the next line, opening curly brace, and hit enter. So what we need to do first is update the winning t value or the nearest t value. So let's set the nearest t to be the t that we got back from the intersectSphere function, and semicolon. This line right here updates the nearest t value. And so we keep a running record of the nearest value that we get back from all the objects in the scene. So if you had like 7 spheres or something, you would do, are you the nearest t? Are you the nearest t? Are you so you ask each sphere if they're the nearest. And if they are, if they beat out all the other spheres, then you update the new record. So then this sphere has the new record, it has the nearest t. And then you keep going down the line of the spheres and you say, do you have one that beats that record? Do you have one that beats that record? Do you? And then, oh yes, this one won, that's closer. So you update it again. So now the new winning record is the t value for that sphere. And so you just go down the list of all your objects in the scene and see who has the winning t value. But in order to do that, you have to keep updating the winning record. So this is what that's doing. So nearest t is now equal to the t that we got back for intersectSphere. And that brings me to another important point, is that this nearest t right now is uninitialized. We just set it to 0 up here, nearest t equals 0. So what we need to do for all the pixels, as we're looping over all the pixels, we need to reset the nearest t. So each pixel, when it starts out, gets a fresh record for the nearest t. And although it's counterintuitive, we're going to make the nearest t start out as the farthest value. So we're going to set it to infinity. And that way, if anything comes back less than infinity, then it'll be the new record. And so we're going to set it to the worst record possible. So let's set it up here right before we call intersectSphere. Go on this line and hit enter. And now let's give this pixel a brand new nearest t to start out with. So nearest t equals infinity. So infinity. We're giving it the worst record possible. So the nearest t is the farthest thing away at this point. And so we put a semicolon at the end there and hit enter. And now as the ray tracer goes through each pixel, it starts out with a nearest t of the worst possible value, so infinity, far away. Now if it hits anything at all in the scene, it's going to come back with a t value that's less than infinity. So if it hits a sphere or the ground or something, immediately it'll win over that poor record of infinity. So it'll update the nearest t to the object that was intersected. And so now that's what will happen here. So say we hit the sphere, then the t value that we get back from intersectSphere will be tested against this nearest t, and that's currently infinity. So obviously it's going to win. And so that becomes the new winning value. So nearest t is equal to t. And now that's the one to beat. And when we do the intersect plane, we have to do the same thing now. We have to test it against the winning record. So let's update this. And instead of infinity, now we need nearest t. And likewise, we have to update the winning t value again. So let's copy this line and update the running record. So paste it there. And maybe let's create a space between these two lines here. That looks a little better. And I'm going to move this over just a little bit. And finally, we have to update this else statement here, because at this point, it will only follow this else clause if it fails this check. But we need to do this if we failed that check also. So how we're going to test for this if it failed all the checks? Well, let's think about this. So nearest t equals infinity. That's what it starts out as. Let's say this one fails and it's not less than nearest t. So that doesn't change. Nearest t is still infinity. And let's say it tries the plane, but it also fails. So the nearest t does not get updated. That means when we get here, the nearest t will still be what it was set to, which is infinity. So it didn't find any objects that won out over its record. So we can check for that here instead of the else statement. Let's say if nearest t still equals, and remember double equals to check for equality, infinity, then we should draw the sky. So a nearest t of infinity after you've checked all the objects in your scene means that you didn't hit anything and you failed all those checks. And so we should just draw the background of the scene. And in our case, we have a nice blue gradient background. And so we're just going to set the color vector to the gradient sky color. And now one more thing to do, we need to actually set the color to the sphere if it passes this sphere test. So if it intersects the sphere and we get a good t value back, then we need to set the color of the pixel to the sphere color. And so we do that simply by copying the sphere color. So color vector dot copy sphere color. And let's add one more space between these two lines here. That'll make it a little neater. And I'm going to add a note up here above this nearest t equals infinity, and just remind ourselves that we have to reset this to infinity for each and every pixel. Otherwise, it'll mess up when it's going from one pixel to the next, because the record will keep getting overwritten as you go from pixel to pixel. But we want each pixel to have a fresh copy of nearest t, that it can see which object will win the final nearest t contest. So, because like I said, if we didn't do anything here and we left that out, then nearest t would compare all the pixels to each other, and that's not what we want. Each pixel needs to be independent, and each pixel needs to have its own record system and its own keeping track of the t value for its own ray, because every ray is different and unique. Okay, with that, it's time for the moment of truth. So let's go into our demo and see if we can see a red sphere. All right, cool. So there's something there that it kind of looks like a sphere, although it's kind of squashed looking, but I'm so happy that we can see a red spherical object in our scene now. So you may be asking, why is the sphere looking squashed? Why is it more wide than it is tall? And that's because we haven't taken into account the aspect ratio of our screen. And so typically on most computer displays, the width is greater than the height of the screen. And so you can see that in this image here, where there is more width to the sphere than there is height, because we have a screen that's wider than it is tall. So we need to take that into account when we fire out each individual ray from each pixel. And basically what it boils down to is scaling the width of the ray directions by the aspect ratio, which is the width divided by the height. So let's go back into the code and add a variable called aspect ratio, and that will represent the width of the screen divided by the height of the screen. So it's the ratio of width to height. So let's go back into intersectSphere.js, and let's go all the way up to the top. And on line 4, let's add a variable called aspect ratio. So let aspect ratio equals, and we can just initialize that to 0. We're going to set it ourselves. And then look for handle window resize, and this handles whenever the program starts up or whenever the user shrinks or expands the window. So each time that happens, we need to gather the width divided by the height and then store that into the aspect ratio variable. So let's do that below this line. So now that we got the canvas.width and the canvas.height, let's compute the aspect ratio. So go on the next line here and then just do aspect ratio equals canvas width, canvas.width divided by canvas.height. And then that was the statement, so semicolon. Now this aspect ratio variable holds the ratio of width to height of our viewport or our drawing area. Now let's scroll down to where we're looping over all the pixels and computing canvas X and canvas Y. And now all we have to do is multiply the canvas X variable, which is left to right, by this aspect ratio. And then we'll have a square space for our viewport, and that'll square everything up and make everything look more symmetrical. So right above this commented line, if row equals 0, let's hit enter and update the canvas X variable. So we're going to multiply canvas x times equals, so multiplication assignment, and then the aspect ratio. So aspect ratio, and then semicolon. And that should take care of everything. So it first computes the aspect ratio when the program starts up, because we call that window resize function at the very beginning of our program. And then once it has that aspect ratio, it comes down here and multiplies it against canvas x. And that scales the canvas x to be more like canvas y. And so then you have more of a symmetrical square space for the rendering to occur. And that should make everything look correct. So now let's head back to our demo and see if that fixed the problem. All right, we did it. Yay. So we now have a perfectly spherical sphere, as they should be, and it appears to be sitting on the ground plane. Now, one thing you might notice is that it kind of appears that it's kind of floating above the ground, and that's because there's no shadows yet. We haven't talked about adding shadows and shadow rays to our programs yet, but I promise we will get to that in the near future. So once we add shadows to a scene like this, it'll look much more like it's really there and it's really sitting on that ground plane. But I'm so happy with this image because that means all of that math that we did earlier and all the functions that we added, the quadratic formula and the intersectSphere functions with all the t values floating around and the nearest t, it's all working perfectly. And so we can clearly see the sphere in front of the ground. So I'm really excited to see this because that means everything is working how we wanted. Now, looking at this image that we've created, you may be wondering, is that really a sphere? It kind of looks like a flat red circle. And you'd be right for having those concerns because the color of the sphere is uniform everywhere. So everywhere where a ray hit a sphere is colored just a simple red color. And what this image lacks is lighting and shading. And that will be the focus of the very next episode. We will take a look at how to light all the objects in our scenes. And once we have the simple lighting calculations set up, then the sphere will appear lighter where the sun hits it, and then it'll appear darker underneath where it's in shadow. And so it'll really pop out then and appear like it's truly 3D. But for now, let's just have some fun now that we know that everything's working and our sphere is being correctly rendered. We can have some fun by moving around the sphere and making the sphere different sizes. So let's try that now. So first, let's make the sphere a little closer to the camera. It's kind of far off in the distance right now, so I want to bring it up a little closer to us. So let's go back up to where we defined the sphere position. Here we see -20 as the z component, and so let's pull it up a little bit by making it something like -10 instead of -20. And remember, the more negative something is, the farther away. So we want to make it less negative, and that'll make it closer to us. So let's try -10 and see what that looks like. Ooh, much better. I like that a lot. So that clearly shows the sphere being rendered on top of the ground, but we don't know if it's on the ground yet because there's no shading or shadows or anything like that. So I promise though we will be doing those things soon. And we'll even add reflections if it's a shiny sphere and things like that. So we will do that eventually. But for today, I'm just really excited that all this is working. So now remember that we had set that L vector to be the sphere position in relation to the ray origin. And that allows us to move around the sphere wherever we like, and the ray tracing will still work, the ray casting. And so now let's move it up and down. So how about a little higher? So how about 5 units up and see what that does? And that's 5 in the y direction. So it's x, y, and z. And positive y direction goes up. Oh, cool. All right. So now it appears like it's a red bouncing ball, and it just has bounced off the ground and it's up in the air. Now let's move it down below the ground and see what happens with that. How about -5? And our plane origin is at -5 also. So now the middle of the sphere is going to be right at the plane. So I'm guessing maybe we're going to see the top half, but not the bottom half. Let's see if that's the case. All right, cool. Now that sort of proves that we're in 3D here, and we're rendering a real 3D sphere and not just a circle. Because if you did that with a circle, it would just be like a semicircle shape. But this is showing that it's sticking out of the ground now, and half of it is below the ground, and then half of the sphere is above the ground. And so that hopefully proves to you that we're really rendering a 3D object here. And with the addition of shading and lighting that we'll do on the next episode, it's going to make it even more realistic. Now let's try moving it left and right and just make sure everything's working how we expect. So remember, to go left, you go negative in the x direction. So let's do -4. Let's see what that looks like. All right, cool. So that moved it over to the left a little bit. And now let's move it over to the right. So +6, let's say. All right, cool. Now it appears a little stretched when you get to the edge of the screen, and that's just a product of ray tracing in general. So when you send out the rays through each pixel, it kind of fans the rays out from the camera. So the camera is like a point in space, or where our eye is. And then it shoots a ray from that eye point to each pixel, and then it goes through the pixel out into the scene. So it goes, if I can do this correctly on my camera, so it starts with the top left pixel, and then it goes like that. But as you notice, when you go out to the edges like this, then those rays are pretty far fanned out. And so that's why this appears a little stretched, because it's still reporting that it hit the sphere, but those rays are a little stretched. So we can fool around with that in the future by changing something called the field of view. And so eventually when we add a real camera to our scene, we can also supply a camera field of view, FOV. And so that will either shrink in the edges of the screen or widen it. So you can widen the field of view or narrow it down. And also with the FOV or field of view, you can zoom into the image or zoom out. So we'll eventually get to that when we implement a camera in a future episode. So let's put it back in the middle now. And I just want to see what happens if we lower it even more. So let's try -7. Now just the top of the sphere is remaining. So that further proves that we're really rendering a sphere. So now it's like if we're above the sphere and looking down on it, and it's below the ground. It's sunk into the concrete. So let's lift it up now and put it back on the ground. And I believe to do that, we have to take into account where the plane is. So the plane is located at -5 down, and then our sphere is 3 units in radius. And so if we want to render our sphere right on the ground, we're going to have to take into account the sphere radius plus the plane origin y value. So how about we do that here, and now that we've set up this plane origin to be this vector here, we can just call that vector's y component and then put it inside the definition of a sphere position. That way, no matter where we move the plane, the sphere will sit on top of it. And so let's add that plane origin dot y. So let's see what happens there. Okay, so now the center of the sphere is right where the plane is. So the center of the sphere is at -5 because the plane origin is at -5 also in the y direction. So that's down 5 units. And so if we want the sphere to sit on top, we have to move it up by its own radius. So whatever the radius is of the sphere, we have to move it up so it'll sit on the ground exactly. And so we can use a variable again and just say plane origin.y and then add the sphere radius itself. So now it'll go find the plane origin and put the sphere right there, but it'll be sticking into the ground. And then we move it up by the sphere radius, and then the bottom of the sphere will exactly touch the top of the plane. Let's go look at that. All right, cool. So now the red sphere is sitting exactly on the plane. And if we moved it down any more, then it would sink into the ground. So if we did like -2 or something, it would sink into the ground just a little bit. See? And if we did +2, that would raise it up in the air 2 units. But it's hard to see that because we don't have shadows yet. So this still appears like it's sitting on the ground, and it's kind of like an optical illusion. But I do like the red sphere kind of like in the middle of the image. So let's move the plane up a little bit, and then that way everything will be more centered. Let's go to the plane and move that up to -3. And then take off this offset. So now we just have plane origin.y, which is -3, plus the sphere radius. And in this case, it's going to be 0 because -3 goes right here, and then sphere radius is +3. So -3 plus +3 is 0. So now the sphere will be kind of moved back to the middle, hopefully. All right, I like that a lot. I think that looks really good. And now let's fool around with the sphere radius. And now that we've set up this use of variables, we can just simply change those variables and this will automatically update. And so let's change the size to 5. Now it'll go in here and redo those calculations where it'll lift up the sphere by its radius and it'll sit on the ground even though it's a different radius now. So let's go check that out. Should be bigger. Yeah, that's cool. So now it's much bigger. Now let's do like a really tiny sphere, so 1. Yeah, so that's like a little marble or something sitting on the ground. And you could even go below that, so you could make it, really, really small, 0.1. That would be like really small. Yeah, so there it is. So now let's go back to 3. I think that was a good radius for this image. So let's go back to 3. That looks great. All right. So, oh, and one last thing, let's try changing the color of the sphere and make sure that's working correctly also. So let's make it a blue color. I'm going to change the 0.8 to 0.01. And then let's go to the blue channel, so it's RGB, so it's the third number. And then let's make that 0.8. And it should be a bright blue now. All right, really cool, great. And you can have fun with this on your own, just experiment with different colors. Oh, and now that we instrumented this differently, with the gradient sky color variable that gets calculated, we can actually change the sky color and the fog color, and those will update as well. So let's try a different sky color. I'm just going to comment this out so we remember what we put here. So new vector 3 opening parenthesis and then semicolon, and then inside the parenthesis let's do like a purple sky. So 0.5 comma 0.1, not much green, and then 0.7, a little more blue. So it should be like a purplish color now. Isn't that cool? So just by changing those variables around and adding that gradient sky color to our mix, we have the ability now to change the atmosphere color. So we can travel to different planets now. So let's go back to our blue sky. All right, and so let's change the sphere back to red now. So we'll give it 0.8 in the red channel and then 0.01 in the other channels, the green and the blue channels. All right, there's our nice red sphere again. I think I'm going to leave it like this for today. I'm really happy with how all this turned out. Remember way back when I said that coloring your first pixel on the screen is kind of like a rite of passage for graphics programmers? Well, raycasting a sphere like this and rendering your first sphere in 3D is a rite of passage for a ray tracing programmer. And so you should feel proud at this point, because now we have the ability to ray trace both planes and spheres. And just using those two simple shapes, we can create a wide variety of scenes that are in the style of the earliest ray tracers from the 1980s. And that's because those historic ray tracers primarily used spheres and planes to compose their scenes. And so I'm really happy with how everything turned out today. And after this episode is over, I'm going to upload this demo here that we did today, as well as the source code, to our GitHub repo, which is the Joy of Ray Tracing repo on GitHub. And the link for that is always in the descriptions of these videos. And so you can go there and then try out all the demos that we've done in the past. And you can also see all the source code, as well as download the source code and then play around with it on your own. All right, I hope you had fun with me today in learning how to raycast your very first sphere. As I mentioned a moment ago, rendering your first sphere is a rite of passage for ray tracing programmers. And so you should feel proud at this point, because now you have the ability to not only raycast a plane, but now you have the ability to raycast a sphere in any location in the scene and of any size and color. And now that we're successfully rendering planes and spheres, we can use those simple shapes to compose scenes that are in the style of the earliest ray tracers from the 1980s. And so once we learn how to add lighting and shading and shadows and reflections to our scenes, we'll be able to create the look and feel of those iconic ray traced images. So on the next episode, we are going to take a look at how to light and shade our objects. In particular, we'll learn how we can find and use the surface normal for our objects, and using those surface normals, we'll be able to correctly light and shade all of the objects in our scene. And that will make them look even more realistic and make the objects appear truly 3D. So I'm really excited to get to lighting and shading on the next episode. So I'll see you next time.